Welcome to our global audience. I was just actually interacting in our Slack, and there's people from all over the world, and we too, your hosts, are also coming to you from myself here in California, and Liz coming to you from the UK.
Yeah, hi everyone, and welcome to eBPF Summit 2024. It's kind of hard to believe this is the 5th edition of eBPF Summit. Yeah, we've got a few bees around, going to be showing a few more surprise bees. If you've got bees where you are, take a photo, put it in Slack. We'd love to see. Yeah, this is EB. We love EB. Welcome to eBPF Summit. That's a bee.
Yeah, it's a bunch. It's a big one. I love it.
Fantastic. So my name's Liz Rice. I'm joined by my wonderful colleague and friend Duffy Cooley, and we are going to be your hosts for today's what we believe is going to be an awesome summit, an awesome event. But before we get started with all the amazing talks and content, we do have a little bit of housekeeping to go through. So let's just bring up a few housekeeping slides.
Yeah. So as we've done in the years past, we do have our Slack instance ready to welcome you. If you go to ebpf.io/Slack, you can log into it and you can join the channel, eBPF Summit channel, where all of the great stuff is happening. And you can interact with us live there. You can interact with each other. And as we proceed through the process, we're going to actually also welcome you to ask questions and interact with our speakers.
Yeah, absolutely. The eBPF Summit Slack channel is going to have a thread for questions and answers for all of our speakers today. I've already seen quite a few of our speakers in the Slack channel saying hello. So I know they're going to be delighted to get questions from the audience. So when you see the thread going into that Slack channel, that's your cue to start asking questions. In previous years, we've seen that chat, the Q&A go on sort of late into the night. So it's really great to see so much interaction amongst the community.
This summit, as in years past again, is actually held to our code of conduct. And to hear more information or to read more information about a code of conduct, you can go to this URL, isogo.to/COC, to read in more detail. But at a high level, the key parts are: be human, be kind, be welcoming, make everyone feel like they are also part of this amazing community.
Yeah, absolutely. And we know there's going to be some great content coming up today. Please be, kind to our speakers who've put so much effort into creating these talks that we're going to see today and sharing their ideas and experiences with us. So speaking of the schedule for today's talk, you can find the list of everything that's coming up at ebpf.io/summit 2024 schedule. There's also a link to that from the summit homepage. And I think there's a link on the YouTube page that you'll find it. There's going to be some amazing talks coming up. Just want to give you a little preview of the keynotes that we're going to have today. So coming up very shortly, we're going to be hearing from Shweta Saraf from Netflix. She's going to be inviting us to consider what the world would look like without eBPF. After that, we're going to be joined by Thomas Graf, our friend and colleague at Isovalent, and he's going to be discussing the eBPF innovation roadmap looking ahead. We're going to have another almost 20 more talks before the final keynote of the day, which is going to be Johannes Bechberger from SAP. He's going to be sharing the experiences of writing a Linux scheduler in Java with eBPF. And I've got to say, Java and eBPF is a whole new concept for me. So that's going to be pretty interesting.
And then I think a lot of our favorite part is going to be what's happening with Capture the Flag. And that briefing will happen at 9:10 Pacific and 6:10 Central. And it's just going to be another really great one. I do have to say that I think the bees have been a little out of hand this year. Dan might have gotten a little crazy. So I'm super excited to see how everybody does with this one this year.
Absolutely. Speaking of bees, I remembered another little bee that I wanted to show everyone, which is on my hand. I actually have a bee.
What? I love it.
Okay, wonderful. So amazingly enough, we are not running behind schedule, which is fantastic. I know Shweta is already in the Slack channel. So I think we should just go ahead and hear our first keynote. Please give a massive round of emoji applause in Slack for Shweta Saraf from Netflix, who's going to be talking about what the world would look like without eBPF.
Good morning, everyone. I'm really excited to welcome you all at the eBPF Summit this year. I'm Shweta Saraf, and I'm here to take you on a thought provoking journey of imagining a world without eBPF. It's unthinkable, right? On one hand, we are so used to all the possibilities that eBPF has unlocked, and it's hard to imagine a world without eBPF unless you have seen the evolution of the technology. But on the other hand, imagining the dark days without eBPF allows you to appreciate how much we owe to this technology and what can we learn from it. So, the first thing that comes to mind is the kernel patching nightmare. The world would be bogged down by long debugging cycles and numerous kernel patches that need to happen without eBPF. This would just result in incremental costs of building software, high CPU usage, high resource usage, and that would just result into a long cycle of frustration and slow development cycle to fix issues that are really complex. The life would look a lot like this Dilbert comic, full of frustration and endless debugging loops would become a daily grind. What about performance bottlenecks in cloud environment? We just assume that it's a given that we have tools that allow us to debug performance on a daily basis. But without eBPF, we would have to rely on good old tools like TCP dump, strace, and in turn, those would require a lot more system resources. They would be highly inefficient, leading us to investing a lot of monetary dollars in monitoring the fleet at a high scale in a cloud environment. Not only the dollar value, but also the operational load of people who are working on these areas would be exponentially higher. So would be the investment in doing metrics or logging efficiently at a high scale. Let's not overlook security. Security is another one where, in large modern microservices based architectures, it can't be an afterthought. It has to be built in from day one. Without eBPF, we would see way more security breaches in large scale infrastructure. Imagine having to deal with slow, clunky IP table based firewalls to debug these issues at scale instead of relying on eBPF. I want to do a shout out to Celium, who has really enabled us to secure microservices based environments with ease. Without them, we would be not be able to do this in a highly efficient manner. My favorite topic, networking. So, in the networking world, Kubernetes and networking would be a nightmare. It would be so manual and error prone, and very high chances of misconfiguration, leading to slower routing of traffic and debugging issues that are already hairy to begin with. We would not be able to leverage deep packet inspection or tracing with ease, and we would need to rely on more intrusive and expensive technologies like traffic mirroring to solve the similar problems. Also, the tools that we take for granted, like sysdig or Tracy, would not be able to run kernel in kernel probes, and overall, just leading to this longer pace of debugging or reaching to a resolution on the network issues. So we don't always know what kind of tools we would need for the future. But if we don't have ability to innovate and iterate faster, it will really hamper the pace at which we innovate. So that's what the world would look like without eBPF. And I want to take a moment to express gratitude to pioneers like Alexei and Daniel who took the Berkeley packet filter and evolved it into the eBPF that we know today, which revolutionized the industry. So you might be wondering, why am I here talking about this? To introduce myself, I have been building platform and products at scale for almost 2 decades in the space of cloud infrastructure and networking. I'm currently the director of platform networking at Netflix. And in past, I have worked on multiple companies ranging from hyperscalers to nimble startups at all stages. My mission in life is to really create the best environment where people can do the best work of their lives. And interestingly, eBPF has been a big part of that journey. So, my journey with eBPF has been rewarding, and it started back in 2015 when eBPF was new and still growing. And I was just very curious about what eBPF could enable as the industry was catching on to this momentum. So, my first use case with eBPF was back in 2017 when I worked at DigitalOcean, a cloud provider specially designed for developers, where we were implementing a rate limiter to access internal services over the virtual network. The virtual network was built with Open vSwitch, and what eBPF enabled us to do was iterate very quickly on how can we do high scale rate limiting for access for these millions of droplets that run on top of it. It was really magical to see how fast the engineers could come up with the solution and productionize it. Fast forward to 2020, I joined another cloud provider, Packet, and we were in the business of running bare metal cloud. So, an interesting thing happened when Packet got acquired by Equinix and became Equinix Metal. We were partnering with CNCF to run an open source partner program. And as part of that, we were donating a lot of these bare metal servers to Cilium devs who wanted to test their code in a safe way, in an isolated way, where performance, isolation, and security were important constraints. So, a lot of devs benefited from that, and it was a really interesting project. In 2023, I joined Netflix, and I'm grateful to serve on the eBPF Foundation board as the Netflix representative. So, lot of the revolutionary work in eBPF observability space that was started by Brendan Gregg began at Netflix. So, after he left and when I joined, I'm doing my own small part to keep the torch alive and continue the work on eBPF across the board at Netflix. So, last year has been a year of experimentation with eBPF for us. We are doing a lot more hack days and ideathons, and a lot of ideas have come through which are betting on this technology and really solving business problems at scale. So, multiple use cases have emerged, and some of those use cases are now running in production. And in 2024, we continue to also contribute back to the eBPF community by open sourcing some of these tools that are coming out of this team. So you might be wondering, what is the eBPF Foundation all about? It was created to create this cross-platform for eBPF related projects for the open source community to come together and collaborate in an independent way. So one of the cool things that I get to do is the recent partnership we did with the BSc members to allocate grants for research in eBPF in academic projects. And I'm proud to say that we got 50 plus applications, and these were the 5 projects that were selected this year for the grants. So now I'm going to tell you a little bit about the Netflix eBPF story that has evolved in the last few years. So the first interesting use case for us is the network observability sidecar. Why? Because Netflix is a very large distributed system ecosystem built on top of AWS cloud. We have needs around understanding the network availability and network segmentation in such a large, complex environment so that we are, as a network team, able to debug these issues very quickly and serve our customers who rely on us. Overall, cloud infrastructure visibility and understanding the priority in which the traffic flows across different clusters is an important use case as well. We collect all of this data and also use it for traffic forecasting and running it through a large ML model, which in turns allows us to do interesting things like traffic shaping and dynamically addressing traffic. So, just to give you an idea, we are at 1 billion flows per day that go through this flow exporter sidecar. And that's the amount of data that we are able to process and ingest and infer insights from. So, this is how it roughly works. We have different systems and different compute environments where this sidecar is running. And the flow exporter sidecar flows into flow collector, where eBPF comes in really handy to achieve efficiencies of scale. And in turn, this data is piped into a big data store like Druid, where the data is then available for different partners and teams to use it in a democratized fashion for the use cases that I just mentioned. So, the next use case, let's talk about noisy neighbor detection. This is a very common problem in high scale compute environments. And we are trying to leverage eBPF for compute use cases at Netflix. So, one of the interesting things here is to instrument the kernel and understand more about the Linux scheduler in an efficient way. By doing so, we are able to detect these noisy neighbor problems, which in turn can be really bad for application performance if not detected and remediated. By doing so, we are able to invest in CPU isolation strategies across our multi tenant compute fleet. And we expect to invest more in this area through the leverage that we get from eBPF. So, if you're interested in learning more about this, a Netflix blog went live yesterday, which was written by our compute and performance teams. So, do check it out how we are leveraging this. The next one I want to talk about is BPF Top. I want to give a shout out to Jose Fernandez, who really identified that we are missing a tool which can do real time eBPF monitoring. So, like, who's really watching the watchers, right? And Jose went and created this dynamic real time view of eBPF programs that BPF Top can provide. It spits out stats like average execution runtime, events per seconds, CPU utilization. And since it has been released about 6 months back, it got rapid adoption in the industry. We saw multiple GitHub stars and forks to the project, as well as a lot of hits on the hacker rank. So, if you're already using eBPF in your fleet, then do consider using this tool, which is open sourced, to monitor your fleet more efficiently. So, next use case I want to talk about is Dropio, which is a rapid fire DDoS mitigation tool that we have built in recent times. So, for a minute, to understand why this is important, we process millions of packets per second that enter through the front door of Netflix. And it's really important to protect our entire fleet from DDoS attacks that are very commonplace these days. In order to do so, it's important to do it faster, more efficiently, and do it closer to the edge as much as possible. So, we invested in building this eBPF based module that is actually highly efficient in enforcing IP based rules and is essentially a user space program that polls for the rules engine, marshals it to the kernel, and kernel performs the enforcement and sends back the results to the user space program. Pretty simple. But what it really enables for us is dropping the packets very early at the XDP eBPF layer without having to traverse the whole network stack, thus saving a lot of resources that are needed in the process. So the early results have been really impressive, And what we see is Doppio consumes only 4% of CPU for the same amount of packets per second that we would have to process in previous rejection mechanisms at the L4 or the L7 layer. So these wins are not only important from an efficiency standpoint, but they are also important for us to have the safety and reliability of running our fleet and protecting us from DDoS attacks so that you can continue to watch your favorite Netflix show without any interruptions. So I hope this was useful. And again, I'm really grateful that we don't have to imagine a world without eBPF, and the future generations will benefit from eBPF for years to come. Thank you.
Thank you, Shweta, and thank you to everyone who's interacting in the Slack, telling us where you're all from. It's just been an amazing thing to see like such a global audience, and also so many people asking questions, and really interesting questions, and really interesting interaction for Shweta in the Slack. Our next keynote is from Thomas Graf, our CTO here at Isovalent. He's going to be talking about looking ahead, the eBPF innovation roadmap.
Hello and welcome. My name is Thomas Graf. I'm CTO and co-founder of Isovalent, and I would like to give all of you a very warm welcome to this year's eBPF Summit. This year, I would like to take an opportunity and look ahead and talk about opportunities and challenges on eBPF's roadmap in the next couple of years. As co-founder and CTO of Isovalent, or as Isovalent more broadly, we have been very involved in eBPF since its creation in 2014, and we have launched an open source projects like Cilium, Tetragon, and Hubble. So overall, a lot of involvement. One could even say that a lot of our company's mission and vision was very tightly connected to eBPF. So let's look at what we see, what I see as the future roadmap of eBPF in terms of opportunities it has. If this is your first summit, or if this is the first time you have an encounter with eBPF, what is eBPF? So here is very quick introduction, 1 minute. eBPF is an efficient and a secure virtual machine running eBPF bytecode. So look at the picture, you see assembly code that can run as part of the operating system. So think about it as a module code that can run. By doing so, it is making the operating system programmable. What's important is it can make that, or it does that in a very efficient and a very secure fashion. In particular, the secure aspect, highly important, as we all learned in the last couple of months, where we saw the devastating effect if a kernel extension is able to crash the operating system. So with this engine, with this virtual machine, with this runtime, able to run eBPF bytecode, an entire wave of networking, security, and observability toolings have been created, leveraging these superpowers of eBPF. And throughout this year's summit, you will hear many, many examples of what exactly is it that eBPF unlocked for them, like projects, solutions, tools that you have all created. You will hear about a very, very wide set of applications of eBPF. Besides this summit, if you are new, then I think the eBPF documentary is also a great way to get a first amount of information. The documentary available on YouTube, so you can just Google eBPF documentary or go on ebpfdocumentary.com and watch the 30-minute documentary on eBPF. It will go back in time and tell you the creation story with the people involved, how the tech giants came in, how it all worked, how we convinced the Linux kernel community to even merge eBPF. Lots of great and funny stories along the way. It's 30 minutes, but it will not feel like 30 minutes at all. Definitely a popcorn-worthy movie. Before we now look into the future, I want to take a moment to highlight what was the single most important aspect of why we even created eBPF. And for me, that is eBPF enabling rapid innovation. I think it's crucial to understand this because it really defines the future roadmap of eBPF as well. So think back, 2014, 10 years ago, Linux had just become the standard or the designated standard for the new operating system running on servers. Like many of us kernel developers, we got excited because all of a sudden, all the development times we built or we put into our hobby developing Linux, all of a sudden this software project was destined to run on thousands, 10,000s, hundreds of thousands of servers worldwide. So a lot of popularity, a lot of success, amazing. But it also had a downside. All of these people wanting to run Linux at scale and in highly efficient mission-critical environments obviously wanted Linux to become boring, stable, and change is a natural enemy of stability and boring. So Linux became slower and eventually slow. And what used to take days now took months, bringing a concept, a new idea, and write kernel code, getting that merged into the upstream Linux kernel and making that available for end users or for end users to even adopt these new Linux kernel versions took months, in some extreme cases, even years. And obviously that really slowed down innovation. eBPF has fundamentally re-enabled that rapid feature development from months back to days, right? What used to take months, we could now write an eBPF program, load it dynamically, execute it securely, and all of a sudden we have extended the Linux kernel on the fly, on demand. And this really brought a wave of eBPF-based super innovation. So think about the bees carrying the snail that got slower and slower, carrying tooks, like eBPF bees carrying the snail and allowing it to go really, really fast again. So that's what got us here. That was the last 10 years, and obviously that still dictates the forward direction. eBPF is amazing at enabling rapid innovation for infrastructure and for tooling at the operating system level. So looking ahead, what else is on the roadmap? What else can we use as challenges, as opportunities? The most obvious one, and probably no longer a big secret, is that eBPF is coming to Windows. So if you Google for eBPF for Windows, you will find a Git repository that has eBPF code able to run on the Windows operating system. eBPF was specifically written for Linux, and it evolved inside of the Linux kernel. The name suggests that it's coming from the BSD days, and that's accurate. There was a DPF implementation that even made it into Linux, all BSD based. eBPF really was a new implementation from scratch and then made compatible to also run legacy BPF programs or classic BPF programs. So that Linux-specific eBPF runtime and the ecosystem is now being ported over to Windows. Now that will not look exactly the same. It will bring compatibility in terms of bytecode, so the bytecode language will be the same. It will also, of course, have a verification concept, and will have things like just-in-time compilation and so on, or once eBPF bytecode signatures are common. All of these concepts are identical and the same, but the actual hook points where eBPF programs can attach may actually be slightly different depending on the operating system. So that also means that we need to bring the existing tooling that we have done, eBPF-based tooling, written for Linux, and also port that over to Windows. So that's exciting. It gives us more reach. All the tooling we have developed for Linux, they will become available or can be made available on Windows over the coming years, and that will keep many of us busy from that front. That's exciting, lots of reach. That popularity, that additional success obviously also comes at a particular cost. So that means that as an eBPF ecosystem, we have to ensure that all the tools we're writing are compatible, right? End users do not want to think about whether one tool is compatible to another one, or I can only use tool A, but not with tool B, and so on. Tools will need to be compatible. Like many tools are coming to the market or are published or open sourced every year based on eBPF. Amazing. All of you have so many great ideas that you implement. These tools often then rely on the same hook points, or they implement even the same ideas. We need to come together and make sure that these tools become compatible, and we solve the problem of interoperability or compatibility. You can also see that there is OSS code will continue to be the standardizing body on the slide here. What do I mean by that? By that I mean that eBPF is a classic example where we didn't write the standard specification first and then implemented the code. We actually did the opposite, the reverse. We evolved eBPF as an open source project as part of the kernel, and the code became the standard. We're now standardizing eBPF, or eBPF is being standardized as part of the IETF, but it's based on the open source code. And the open source code will remain to be the source of truth, where the actual standard is evolving, where we have the discussions and the consensus finding. That will not change, right? So that means as a community, we have to come together, figure out how do we make tools compatible to each other, how do we make tools portable from one operating system to the next. So exciting, that's a bit of a challenge. We need to solve this. It's something to unlock for the next wave of eBPF tooling. It's a cost of the success of eBPF. If you look a little bit further, what else is on the horizon? And one topic is very obvious, AI. And I'll put an asterisk right there, right? Because I don't necessarily mean that we need to use AI for eBPF. If you have ideas and you want to explore that, go for it. I think can be very exciting. But there is even just a broader industry, I would say, movement that will happen completely disconnected to how successful AI will be. There's currently a large investment into GPUs and DPUs, and you can see that when you look at the NVIDIA stock for sure, right? So instead of just deploying CPUs, companies around the world are now also deploying GPUs, graphical processing units, and DPUs, data processing units, specifically to enable AI workloads in the future. And this investment is happening, and it is happening completely disconnected from the fact whether the AI wave will actually produce something really, really meaningful or not. The opportunity is so big that the industry will try. So this will happen. It will result in an entire new wave of infrastructure getting deployed that is not just CPUs anymore, but is more specialized hardware with GPUs and DPUs. And that new infrastructure layer with more capabilities will drive demand for rapid innovation in that infrastructure. So all the goodness that eBPF brought for the age of CPU only will need to get reapplied for the age of CPU plus GPU plus DPU. And this is where eBPF will be able to come in and again illustrate and demonstrate its superpowers applied to GPUs and DPUs. Last but not least, the outlook that keeps me most excited is what I call eBPF distributed intelligence, which is a completely made up word. I don't think that's an official term in any way, but think about it this way. So far, any sort of intelligent behavior or analytics or even machine learning use cases, anytime we try to apply some smartness, the typical architecture we have been using so far is we have compute with applications running, infrastructure running, and then we have relatively dumb data collectors that will stream a lot of observability or telemetry to an analytics database. This can be an SIM, can be a time series database, it can be a graph database, whatever it is. A lot of data gets streamed into these databases and we keep a record of the history, and then we look at that data and we make decisions based on that data. We run analytics or we learn, right? That's the model that's been dominant so far. And it's a model that works, but it will eventually stop scaling because it results in a massive amount of data being needed to be transferred. And it has massive storage requirements as well. And we're now at the point where the amount of intelligence that can be applied is limited by your budget for data transfer and storage requirements, or just the scaling abilities of databases. Well, what if we could turn this around and we can say, instead of bringing the data to the intelligence, we bring the intelligence to the data. So think as eBPF as giving us the opportunity to not just have very deep observability, but to also essentially only extract the observability we need and then apply logic to make intelligent decisions and react to that. Ways that don't require us to stream data somewhere else and then react there, but to essentially make a decision, an intelligent, smart decision on the fly based on the context we have available at where the source of the data actually lies. This will not work for all types of use cases. There will be use cases that do require this completely distributed view over observability samples from all sorts of edge nodes and so on. But for a lot of use cases, bringing the intelligence to this data will be way more efficient. It will lead to new security, networking, observability monitoring tools that are more efficient, faster reaction times, and in the end will result in better infrastructure for all users. So that's what keeps me very excited for the next coming years. I think this will be an area where eBPF will really shine, and where we will see not just rapid innovation, but also application of eBPF's logic ability. And with that, I would like to say I'm really looking forward to continue innovating with all of you. I would love for you all to reach out to me, ping me on Slack, ping me on LinkedIn. I would love to hear, are you agreeing? Are you disagreeing? What are you excited about? What keeps you excited about eBPF? What are ideas you have? I would love to learn from you and continue the conversation. With that, I would like to thank you all very much and want to wish you a continued successful, funny eBPF summit. And I'm looking forward to answering questions on Slack. Thank you very much.
That was a really great talk from Thomas, I thought. Lots of thoughts being provoked. I can see lots of really, people being really excited about the idea of eBPF for Windows as well. If you go to Slack and check out some of the links that have been posted there to things like the eBPF for Windows project. Thomas also mentioned the eBPF documentary, which I've got the poster for there behind me. Somebody has also posted the link to that documentary in YouTube. Highly recommend it if you want to get the backstory on eBPF. But I thought one of the really interesting things about Thomas's talk there was how, it's making us think about the future. It's making us think about some of the problems that could be solved with eBPF. So maybe that's put us in a problem-solving mood, which means it would be a good time to start talking about the capture the flag. So let me welcome Dan Finneran, who has been responsible for building this year's really rather amazing Capture the Flag Challenge. Hi, Dan. Dan, you're muted. Oh, technical issues. Okay, well, Dan sorts out his microphone issues. And this is so strange because we were online earlier. While Dan sorts out his microphone, I will mention that the URL for the Capture the Flag is on the screen. It's basically isogo.to/CTF 2024. That will take you to, it's GitHub isovalent/eBPF Summit 2024 CTF, I think it is. You'll find it. We'll post the link in Slack. And you're going to find all the instructions that you need there and all of the kind of configuration for the virtual machine. I'm feeling really bad for Dan right now, who's clearly struggling with the technical issues. Okay. I will mention that I had an opportunity to test out the Capture the Flag challenges. They're really good. They start off quite straightforward, so you can use some familiar online tools, but they do build up to some really quite challenging problems that I think you're going to need to write code. So, we've gone from things you can do at the command line to some things where you're really going to have to get some C code out. Hi, Duffy. You're going to take the place of Dan.
I'm going to take the place of Dan for a little while anyway. But we'll have him back here in a little bit. I was going to say, don't forget that we do also have Slack channels for this sort of stuff. So if you're looking for help, or if you're looking for more information, yeah, like we're going to have, you can interact with the CTF in the general chat. And if you're curious about spoilers, some people are not. Some people want to just like try it on their own. But if you want to also just share like some interesting way that you're solving a problem, or share some ideas or help others, you can actually go to the eBPF Summit CTF or the eBPF CTF Spoilers channel, and where you can kind of interact and do that part of it.
Yeah, please only put spoilers into that spoilers channel. Don't put spoilers. Don't tell anybody about how you've solved it into the main channel. And ideally, in that spoilers channel, you can create a thread, and then you can kind of hide your spoiler underneath a thread, and then that's kind of nice for everybody who wants to be able to solve as much as they can without your assistance.
For sure. Another interesting aspect of this particular CTF is that it's hosted on your machine, not anywhere else. It's actually going to be using Lima, so you can actually just run this in a VM. It'll be with its own kernel, nothing that is going to mess with your underlying system. You should have a really great time kind of exploring all the different flags. It's going to be really awesome. Feel free to help each other, and feel free to interact that way. It should be super cool.
Yeah, for sure. And the nice thing about that Lima VM config is, everybody's got the same setup. So, we have a kernel version that's going to work with this challenge. So fingers crossed, it's going to work for everyone. It works on my machine. So yeah, good luck everyone taking part in the Capture the Flag. Hopefully we will resolve Dan's mic issues. He's going to come back later on in the day to report back on how everyone's been getting on. So if you do solve the problem, post the result that you get in the appropriate channel, and we will know that you have managed to solve all those challenges. One last shout out that I want to make is to our friend Quentin Monet, who has continued the storyline. If you've been a long time attendee of the eBPF Summit, you'll know that every Capture the Flag challenge has this amazing backstory that's sort of a little bit Star Wars-like, and Quentin has carried on that theme for us this year as well. So thanks, Quentin. We really appreciate it. Everyone, do go and enjoy that Capture the Flag. We are going to give you a few minutes to check that out. We're going to take a break. So it's a great opportunity to take a look at the Capture the Flag. We will be back at 20 past the hour for the next series of talks. So go check out the CTF, have a break, have a stretch, and we will see you very soon.
Have a lot of fun. It's so great to see so many of you interacting live in this session. The Slack is absolutely buzzing with excitement. It's absolutely great. In this next section, we're going to have, I believe it's 6 talks. And in these 6 talks, we're going to be talking about something that is core to eBPF itself, the idea of eBPF and networking. There are a number of really great talks talking about it. The first one we have is from Nick Zavaritsky, and it's entitled, We Write Our Applications in eBPF, a Tale from a Telecom Operator. Welcome, Nick.
Hi, I'm Nick. I work for a company called Amnify. I'd like to use a cute example to explain what we are doing. I have a customer that makes smart mouse straps. Once a mouse is strapped, a push notification is sent. The mouse strap is always online and it doesn't depend on your Wi-Fi for connectivity because it has Amnify SIM inside. We don't offer voice, only data. Shipping IP packets is an important part of our business. We relied on DPDK in the past, but now we are transitioning to eBPF. Today, I want to tell you why we see eBPF as a game changer. I'd like to acknowledge that signaling in cellular networks is a complex topic. I will conveniently ignore signaling today. Once a device is online and authenticated, the data path is rather simple. It is a GTP tunnel we have to terminate. On the right-hand side, we have AWS integration. Device traffic gets right into the customer's VPC without traveling over the public internet. Actually, it enters our VPC first. The traffic is wrapped in GRE because AWS Transit Gateway understands GRE and it can match the tunnel to the customer's VPC we are pairing with. We had to convert between GTP tunnels on the left-hand side and GRE on the right-hand side. We have over 1 million GTP tunnels in a busy region, but relatively few GRE tunnels. Clearly, you can't have a million tunnels in Linux. Instead, a single tunnel in so-called collect mode aggregates all GTP traffic. A TC program uses BPF SKB get tunnel key helper to recover information about a tunnel. The program uses BPF maps to match a tunnel to the customer and to find out the target GRE tunnel. Finally, the program updates the tunnel key and redirects the packet into a GRE device, also operating in collect mode. It's reasonably fast. Better yet, it handles all complex corner cases, such as packet reassembly and fragmentation and sending ICMP fragmentation needed messages. Corner cases do happen, but for the majority of packets, conversion between GTP and GRE is as simple as changing a few headers in the packet buffer. We use XDP program for the fast path. It matches a tunnel to the customer and finds out the target GRE tunnel using eBPF maps shared with TC program. So apparently, eBPF is quite handy and powerful. However, we consider it a breakthrough for a different reason. Let's have a look at the broader picture. There are some complications. On the left, a device can open several sessions simultaneously. It results in multiple GTP tunnels to be used for different traffic classes. On the right, it is typically a few GRE tunnels per customer for improved throughput and redundancy. Some customers do their own tunneling so that packets can carry additional metadata, such as an endpoint ID. And in between, we have a NAT and a firewall and flow logs and a kitchen sink. Due to overall complexity, we prefer to do several apps instead of a single monolith. So we have multiple apps to operate, and not just multiple apps, but multiple instances of every app. It would be nice if we could run several apps side by side on a single server. Another challenge is state. Product evolves and requirements change, therefore we have to push updates often. But the tunnel might live for days. Either we keep old versions of the software around until it drains, or we impact customers. It would be nice if we could extract state out of a running instance and somehow inject it into a new one. With eBPF, it is finally possible to run multiple packet processing apps side by side. That's why we write our applications in eBPF, or more precisely, the packet processing part. We use Golang for user space part. We are happy Cilium eBPF users. We manage our fleet with Kubernetes. I have to acknowledge that eBPF maps are accidentally awesome. They are equipped with powerful API to populate. and to read back the content. Speaking of content, a complete type information is available. It is not opaque bytes you are looking at, but rather structures with named fields of known type. It is possible to build a generic tool to dump and restore state, performing conversion if that data layout changed. With sufficient effort, streaming replication can be achieved. We can also populate a eBPF map from a database table in a generic way. I'd love to dedicate more time to eBPF maps, but unfortunately I can't. Speaking about high-performance packet processing, it's hard to ignore DPDK. It has been around for a while, and it is quite popular. The idea is to remove a network interface from the kernel and to drive it from user space. Packet buffers are shared with user space via memory mapping. Similarly, receive and transmit rings are exposed. Application pulls receive ring in a busy loop to find out if there is an incoming packet. I have to acknowledge that DPDK in general is faster than eBPF. A modern CPU has many special-purpose instructions, such as AVX, which eBPF lacks. When using DPDK, a CPU core is typically dedicated to a single task. Hence, CPU cache hit rates are higher. DPDK is also more flexible since it is just regular user space. However, DPDK means busy polling. As soon as there are more threads than CPU cores, everything falls apart. With eBPF, it is possible to run multiple packet processing apps side by side easily, and it is huge. Finally, let's talk about running in Kubernetes. An application relying on XDP works just fine in Kubernetes, except it doesn't. An XDP program won't see any packets coming in. It doesn't work with virtual Ethernet pairs. It probably doesn't work with Netkit either. Let's follow the path of an incoming packet. A TC program attached to ETH0 observes a packet and redirects it into VF1. Normally, a redirect would put a packet on an internal queue inside virtual Ethernet pair, and packet processing would end. Eventually, the kernel will find out that there is a packet pending. The packet will re-emerge from VF2, passing through SDP and TC layers as expected. But there is an important optimization happening. Instead of a plain redirect, PBF redirect peer is done. The packet doesn't go into a queue. The packet processing doesn't end. Instead, it performs another iteration with ingress interface set to VS2. Since there is no waiting on the queue, the latency improves. Several corners are cut and SDP is skipped. However, for our packet processing needs, we actually want the packet to get on a queue. Consider this. We have many packet processing apps, each with their own eBPF blobs. Accumulating multiple packets and processing the batch together is more effective from CPU cache perspective. We'd also like to dispatch packets to pods in XDP, since going through TC to hit XDP makes little sense. Apparently, packet processing apps have different needs compared to regular container workloads. Since we don't see a way to unify conflicting requirements, we provision a secondary interface with a custom CNI. It's time for a conclusion. We are taking smart devices online using XDP and TC. The service is complex, therefore we are doing several apps instead of a monolith. With eBPF, it is finally possible to run multiple packet processing apps side by side. It is really cool. However, to make it work in Kubernetes, a proposed build CNI is necessary. We are currently working on one.
BPF maps are awesome. I completely agree. It's an amazing thing. There's a lot of really great stuff in that talk, talking about both the complexity of kind of. I was thinking it kind of resonates a little bit with Thomas's talk about bringing the intelligence to the data, right? Like here we're trying to actually mux between different types of user sessions, and I thought that was actually pretty cool. Thank you very much, Nick, for that amazing talk. There'll be a thread in there where you can interact with Nick and ask questions or provide comments. Our very next talk is going to be from Nikhil Malik talking about end-to-end SCTP multi-homing with eBPF.
Hello everyone, I'm Nikhil Malik, working as a principal engineer in Netlog, South Korea. The topic of this talk is end-to-end SCTP multi-homing with eBPF. In this talk, we will briefly touch upon basics about SCTP, multi-homing, and related problems with load balancers, why we chose eBPF to implement SCTP multi-homing, and how we leveraged it. Next, what all challenges we faced with eBPF, and at last, some performance analysis. HTTP protocol with multi-homing enhances the robustness, reliability, and efficiency of network communications across various applications, making it a valuable protocol choice in modern networking areas. As the networking world has evolved to cloud-native deployments and microservices in the cloud platforms such as Kubernetes, introduction of stateful load balancer for hosting services has introduced many challenges, especially for multi-homing features. The problem persists with monolithic systems with standard stateful load balancers as well. When SCTP connection establishes, most of the stateful load balancers track the connection and maintain only the primary address information about SCTP endpoints, unable to leverage core offerings of SCTP multi-homing. To support multi-homing, it would be required for a load balancer to host SCTP service with primary and secondary IP address and share them with both the endpoints during SCTP connection establishment. Map load balancer IP addresses with endpoints, primary and secondary IP addresses, manage multiple network paths, calculate checksum after NAT, and most importantly, load balancer should not introduce any significant performance overhead. eBPF technology is a very well-known performance technology which can provide tools and methods for every requirement stated previously. Each SCTP endpoint share its secondary IP information during connection establishment in init and initat packets. Once the primary and secondary IP information has been received from both the SCTP endpoints, then it would be required to map them with the load balancer IP address and stitch a bidirectional path for the traffic. LogCLB uses eBPF maps a key value store to store all the information, which can either be used by eBPF program or its user space application path to take the necessary action on the incoming packet. It takes a multi-transactional update to the eBPF map table to add all the entries related to a particular connection. Although eBPF is the state-of-the-art technology with many benefits, but it has its own challenges such as limited instruction set size, deleting map entry in the loop, limited helper functions for SCTP in the kernel, and it becomes increasingly difficult to calculate CRC32 checksum for big size packets within the limited resources. eBPF allows section where you can have a re-entrant code for checksum calculations and use tail calls to jump back and forth between them and finish the task, but tail calls are costly. So by reducing the number of tail calls and batching packet reads in the chunks in LogCLB, we were able to improve the performance from 242 Mbps to 1.4 Gbps. For further optimizations, we are targeting to replace tail calls with BPF loops. Last year, we presented state synchronization of eBPF maps, where we discussed how state information in eBPF maps can be synchronized with cluster-wide peer entities to provide hitless failover. This year, we extended that infrastructure to support SCTP multi-homing features as well. All the network paths in the SCTP association will now be synced with peers via gRPC. In case the active LogCLB instance goes down, then the connection will not be disrupted as all the eBPF map entries are synced with the peer instance. This is the topology we used for our analysis. We evaluated our solution with Seagull as client and server. Seagull is a multi-protocol traffic generator which is used as a standard to test telco traffic. The aim of these tests was to observe any performance overhead by introducing a load balancer. You can find the description and link to this demo in the comment section. Our first test was standard calls per second where it was set to 5000 CPS. We observed that introducing LogCLB as load balancer did not add any performance overhead. Our next test was to observe and compare the recovery time and rate after the primary network path is down. We observed that path failover time was not impacted by introducing LogCLB, though the recovery rate of failed calls was better with LogCLB. This was because of the LogCLB's eBPF data path capability to process the SCTP packet faster, which helped in clearing the backlog. Lastly, we thank you for your time. Please do visit our GitHub and website to check out more. Thank you.
Awesome talk. Great to see the project LoxCLB happening, and what's happening with like interesting protocols like SCTP, which is a really interesting protocol in obviously in the telecom space and other types of things. Thank you very much for that talk. If you have questions or comments, please again just jump into that thread and provide feedback and welcome Nikhil to the community. Our next talk up is going to be by Nimisha Mehta and Alvaro Ailman, talking about Confluent's multi-cloud journey to Cilium, pitfalls and lessons learned.
Hi, my name is Nimisha. I work as a software engineer at Confluent, and I'm here together with my colleague Alvaro. We are here to share a little about how Confluent migrated to use Cilium on our multi-cloud fleet of Kubernetes clusters. Confluent Cloud is a cloud-based data streaming platform that provides managed services such as Kafka and Flink to help companies process and connect data. It is available on AWS, Azure, and Google Cloud, consisting of applications deployed on thousands of Kubernetes clusters across many regions. We use the cloud provider's managed Kubernetes services, with the default CNIs managing networking in the clusters. We chose to migrate to Cilium for its security features such as transparent encryption, DNS-based network policies, and enhanced observability with Hubble. Another motivation was maintaining a consistent CNI across our fleet and not having to deal with cloud provider-specific behaviors. Additionally, having support from Isovalent for our enterprise Cilium installation made the decision to migrate much easier. There are risks associated with replacing a low-level component like the CNI. The main challenge was doing a live migration on clusters running production workloads without any network disruption or loss of connectivity in the clusters.
So let's talk a bit about the actual migration process, starting with AWS. The way we do this is to set up Cilium only on new nodes while leaving the old one managed by the default AWS CNI. To achieve this, we label new nodes with the CNI equals Cilium label. We then configure the default AWS CNI to have a node selector that does not match this label, and then we install Cilium with node selector that only matches it. Then we bring up new nodes, and because of these selectors, only the new Cilium CNI pods will run on them. The two CNIs can coexist in the same Kubernetes cluster because at the end of the day, they both use AWS native routing. So workloads can communicate with each other regardless of which of the two CNIs is being used. So once the new nodes are up, we clean up the existing ones so all workloads get moved over to Cilium managed nodes. And then once that is done, we delete all nodes with the AWS CNI on them. And once they are all gone, we just delete the AWS CNI altogether from the cluster.
For CNI migration on GCP clusters, we followed more or less the same process of bringing up new nodes with Cilium and migrating workloads onto them. However, the default CNI with GKE called netd is enabled by default when using certain features. A gotcha here is that since netd cannot be uninstalled, a node could become ready even before Cilium has finished configuring it, which means application pods can get scheduled on the node before the Cilium agent. As a result, this can leave some pods unmanaged by Cilium and can lead to multiple pods ending up with the same IP address. On Azure, there is an officially supported migration path as shown here. However, the migration is quite complex and involves transitioning through various CNI configurations, during which nodes have to be replaced multiple times as well. Another important caveat worth mentioning is that with this migration path, you always end up with Cilium using overlay routing instead of native routing. Because this migration path is a little involved and long-running, we did not end up implementing it at Confluent and only install Cilium on new Azure clusters for now.
So to summarize a bit what we've learned, no matter how much testing there is, some issues will realistically only surface in production, like the IP clashes we've seen on GCP. Generally, if you're running a multi-cloud setup, the Cilium configuration will likely not be completely identical across all of them. Versioning it and using GitHub helps a lot with keeping it consistent where possible and being able to pinpoint issues to changes. The integrated unmanaged pod watcher helps with finding unmanaged pods, but unfortunately does pod deletions and not evictions, and as a result will not respect pod disruption budgets. It also pretty much doesn't work in the context of a migration because existing nodes in such a migration by design have no Cilium on them. And we don't want it to just delete everything on these existing old nodes without Cilium and cause a downtime. So basically it cannot be used. An alternate to this is to just monitor pods that are unmanaged by Cilium on nodes that do have Cilium in them, and then alert on them while this migration is ongoing. As always, when finding issues like this, document them for the rest of the team and try to leverage the open source community as much as possible.
Yeah, what a journey! It's great to see that. Great to see them sharing, like, basically what they, what their experience was and all of the work around it. So yeah, just tons of work there. Our thread is live, and Nimisha is in there answering questions. If you have anything you would like to share or questions that you have, definitely jump in there. Our next talk is going to be from Chen Tang and Feng Zhao, Embracing NetKit Across 1 Million Servers. What should we do?
Hi, everyone. My name is Chen, and I'm a software engineer in ByteDance. And today my topic is embracing NetKit across 1 million servers. What should we do? So first, let's give a brief introduction about what is NetKit. NetKit is a new network device like with created in pair, and it can be used in container networking, but it has a much better performance, and it's merged in kernel 6.8. So since we all know that NetKit can achieve a better performance, why not start using it from now? But it's not so easy to use NetKit in a production environment because first, stability is top priority. Nobody has tried NetKit in large scale. And second, even NetKit is attractive, but using kernel 6.8 is difficult because most companies are not so aggressive in adapting new kernel. Taking us, ByteDance, as an example, we plan to use kernel version 6 probably 2 or 3 years later. So far, we're still using kernel version 5. So the first things we need to do to use NetKit is backporting NetKit to the kernel version we are implementing in our data center. And we decide to backport NetKit to kernel version 5.15. And here's the list of features we have backported. The first is NetKit, and is also the TCX feature along with NetKit. And we also try to backport NetKit to kernel version 5.4, but it requires additional backport of BPF link, which leads to other conflicts and a more strict code review. So eventually we decide to choose 5.15. And now, once we have the kernel ready, we need a graceful upgrade because we need both CNI and the kernel upgraded to use NetKit. But the upgrading pace is not aligned because the kernel is upgraded by a different team. So we don't know which one gets upgraded first. If we firstly upgrade CNI, then we upgrade kernel, it's easier because once the machine is rebooted, we have the CNI and kernel both ready, and we can create NetKit for new containers. But if we first create an upgrade kernel, that means at the very beginning, we still create with for new containers. And then once we upgrade CNI, we will create NetKit for later containers. That means we might have with and NetKit coexist in the same node. And then we need compatibilities with pair. So compare with with, what else should be taken care of? First, like I mentioned before, we need compatibilities between NetKit and with. So don't use BPF redirect peer for help functions for NetKit with connections because the packet will get dropped here because the packet is not at the SKB is not at the SKB is not at TC ingress hook point. And second, we also need to manage BPF links for Netkit because it's not attached to TC hook point anymore. It needs BPF links for persistence. And that means we also need to recycle the BPF links once we want to destroy it, the Netkit, the device, or we detach the eBPF. And before we get everything prepared, we also need to handle what if anything bad happens, because at this moment, we cannot guarantee that Netkit works properly as our expected. So what if CNI fails to create new Netkit device? We might fall back to with, or we let the CNI return error to container D, or we create a backdoor for the CNI to stop using Netkit. Or maybe the Netkit creates successfully, but the Netkit eBPF is not functioning. Then we also need to fall back to TC, and we must delete the Netkit eBPF. And so far, we believe that we have everything prepared, and we start to push Netkit and the new kernel version online. And so far, this is our achievement. We have CNI supporting Netkit deployed in dozens of clusters, and the kernel rolling upgrades simultaneously. And so far, we haven't seen any accidents reported related to Netkit. So I'm confident to say that Netkit is trustable. And now let's talk about the benefits of using Netkit. First, we have the expected benefits of using Netkit. We have the improvements in throughput, and we have improvements in the save of CPU usage, but it's all discussed before, so we'll skip this part. Let's come to the next. We have some unexpected benefits of using Netkit, because Netkit unintentionally solves problems resulting from using with, and all these problems are related to the software interrupts in the with backlog queue, since Netkit eliminates software interrupts, and then we don't have this problem anymore. The first is the high CPU load when we're using with. It's a known issue and it's already fixed in the latest kernel, but since we are still using kernel version 5.4 and 5.15, we still have this problem. We have the SKB report RxQ will cause, at the same node, there will be only one core to handle all interrupts from all with device. And why this problem gets solved by Netkit? Because Netkit eliminates software interrupts and the backlog. And the second, we have packet disordered when using with RPS disabled, because we all know packets in the backlog queue which for its standard CPU to handle its software interrupt when RPS is disabled. And the send packets in the container are assigned to different CPUs by the process. So that means all send packets from the container in the backlog will wait for its own CPU to pick it up. But because of the uneven load distribution among CPUs, it might happen that the prior packets may be processed later due to the response time of each software interrupt is different. But this is no longer a problem anymore because, like I said before, Netkit eliminates software interrupt and eliminates the backlogs, and all problems related to this are solved. So actually, it's it is out of our expectation, but we're happy to see the result because we spent a lot of time on this to see if we can find an effective way to solve these problems from with, but it's difficult. But once we migrate from with to Netkit, it's no longer a problem. So I think we are like motivated to widely deploy the Netkit in our data center. And that's all. Thank you.
Amazing. Chen and Fang living in the future. I mean, I can't wait to actually see Netkit become more prevalent in kernels and for us to move forward in time far enough that we can start using Netkit in all of the Kubernetes environments. I know that, like, I was chatting with Thomas about this the other day, and he was saying that early in the project's life, in Cilium's life, they were talking about, like, you know, what if we didn't have to do the beef thing? What if we came up with a different mechanism for this? And so it's just neat to see all of these things kind of coming to fruition over time. But just amazing stuff. So make sure to ask your questions in there and help me welcome Hemant Malla talking about implementing networking QoS for containers with eBPF and Cilium.
Hello, everyone. My name is Hemant. I'm an engineer at Datadog working on the Kubernetes networking team. And today I'll be talking about implementing networking quality of service for containers with eBPF and Cilium. So why do we need networking quality of service? Kubernetes is designed for sharing nodes between different applications and teams, but we cannot really control what your neighbors are doing. So you can have noisy neighbor effect. And in Kubernetes, we do not really have abstractions that allow us to maintain a given quality of service level. So you might apply bandwidth limits on your workloads, but depending on the nature of your application, that might not be flexible enough. Or you may implement bandwidth requests to hint at the Kubernetes scheduler so that the workloads can be spread across multiple nodes, but that's not a perfect solution either. And if you look at hypervisor metrics from cloud providers like ENA bandwidth allowance exceeded in AWS, you'd be surprised to see that the hypervisors drop a lot of packets. And the worst part is the hypervisors decide which packets should be dropped. So can we do better? What if we can prioritize which packets should be dropped under network contention? So let's take a quick look at at a demo to understand how the system works, and then we'll come back to understand how it's built. So I have 3 pods. I have a NetPerf server and then 2 NetPerf clients. The first pod is called high priority client, which has a QoS class set as guaranteed. And I have a low priority pod, which has QoS class set as best effort. So let's see if my pods are running, and the NetPerf server is running on one node, and both the clients are running on a different node. So let's exec into the low priority client on the bottom right and high priority client on the top right. And what I'm going to run here is something called super NetPerf, which basically runs multiple instances of NetPerf and aggregates them, averages them together. And I'm going to run the same thing here to create some network contention. And we'll come back in 2 minutes to see the results. So if you get back to the talk, so the kernel has had support for some kind of quality of service for a long time now. So you can either set the type of service bits on the IPv4 header or very recently called DSCP, but whether those bits are respected or not depends on the kind of packet scheduler you have configured. So for example, Prio and MQ Prio implement something called a strict priority, which can lead to starvation of processes which are classified as low priority. But FQ from 6.7 and above implements something called as weighted round robin. And this is explicitly designed to avoid starvation. So it has 3 priority bands, high, medium, and low. And the weights are designed in such a way that if a high priority pod competes with a low priority pod, the high priority pod gets 90% of the bandwidth. Similarly, if the high priority pod competes with the medium priority pod, the high priority pod gets 75% bandwidth. And if you want to implement a system like this in Cilium, there's another feature that kind of controls how the QoS setup is on the node. And that's Cilium Bandwidth Manager. And Cilium's Bandwidth Manager implements bandwidth management with FQ and earliest departure time compared to using something like token bucket filter. And this allows to avoid a global QoS clock, which has proven to be a lot more CPU efficient. And if you're interested in learning more about it, I would highly recommend either reading Google's Carousel paper or Daniel has a great KubeCon talk. I'll have references to that at the end. So once you enable Cilium Bandwidth Manager, Cilium installs FQ QDisks on every hardware queue on all the physical devices that are managed by Cilium. So thanks to eBPF, we can actually set the priority for every packet by updating the field on the SKB without having to change anything on your application. So how does this entire system look? The user sets a QoS class on their pod, and that annotation is translated into a BPF map. And we have a TC egress BPF program attached to every physical device managed by Cilium. And in that BPF program, we look up the BPF map based on the endpoint ID to get its corresponding priority level. And we set the SKB priority value to make sure that the packet scheduler can enforce those priority class. And this is the customary single slide BPF code changes. We basically update the Cilium's 2NetDev BPF program to look up the BPF map and update the CTX priority value. And here are the references that I was talking about earlier. And if you're interested in looking at the code or giving us any feedback, you can go to pull request 34366, and I appreciate any feedback on it. So now let's go back to the demo to see if our benchmarks are completed. So as you can see here, the low priority, one, I think I have the wrong priority set, but you can see that the 1:9 ratio on 138 and 914.
Awesome. So great to see continuing innovation on the Cilium project and all of that stuff. Thank you very much, Amanth, for that talk. Jump into the Slack thread and ask questions or share your thoughts on that PR, etc. Our next talk and the last talk are going to be from Ashish Kashinath and Tim Baer, talking about adaptive routing with eBPF.
Hello everyone, welcome to our presentation on adaptive routing with eBPF. We are Ashish Kashinath and Tim Baer from UIUC and Aviatrix. Our application domain is in multi-cloud, multi-region cloud computing systems where performance variability and limited visibility is the norm. And in such large-scale systems, typically traditional routing schemes are used, and these schemes are generally best effort schemes with static failover strategies. And in such systems, achieving end-to-end latency guarantees and resiliency, such as steering around failures, is hard. And our goal through this presentation is precisely that. To understand this further, let's look at a small example. Suppose we have a flow with a deadline of 1000 milliseconds. And let's say that 700 milliseconds have passed. And after this, the flow has two choices to make. One is to go via interface 0 and interface 1. And their current and worst case latencies are listed in the table as shown. In such a scenario, most routing schemes would choose interface 0. Why? Because its current latency of 50 milliseconds is less than interface 1's latency of 200 milliseconds. But there is a problem here. The problem is that interface 0's latency of 500 is much larger than interface 1's worst case latency of 250 milliseconds. And so, if there is a service degradation on interface 0 and the new latency is not known yet, then it could lead to loss of performance guarantees. And to solve this, we propose adaptive routing. Adaptive routing is an algorithm that proposes to dynamically steer flows. And the goal of adaptive routing is to find an interface that meets the deadline in the worst case, while in the average case, it provides the best possible performance. Shown in the slide is a code listing of the core adaptive routing algorithm. Here, we have an interface latency eBPF map from the interface index to the corresponding latency metric. We also have latency max and latency current, which correspond to worst case latency and current latency. And then we have the variables now and deadline, wall clock, and the flow completion deadline. In the for loop, we iterate over all the possible interfaces and look up its latency metric in an eBPF map. And then we check for two conditions. Does the interface's worst case latency satisfy the deadline? And does the interface's current latency, is it the best possible current latency? And once these two conditions are checked, we arrive at the best possible interface index, and that is where the traffic is redirected to using the BPF redirect primitive. Our implementation around this algorithm consists of the following. In our packet, we have a custom header for timestamping to track the latency as it flows along the network. Also in the packet are DSCP bits to signal low latency. In our user space program, we use the ping tool to determine the next hop or interface's latency metrics. And our BPF program is attached to the TC egress and comprises of two maps. One is from the interface index to the latency, and another map from a flows 5 tuple to its previously chosen interface. We'll look at the second map in more detail later on in the presentation. And lastly, we have the BPF redirect primitive that is used to redirect a packet to the best interface.
Our first experiment is a comparison of adaptive routing and static ECMP, where we're trying to transfer a small 5 megabyte file. This is a little bit of an adversarial example in the sense that we figure out what interface the TCP connection will be hashed to, and we inject an artificial 500 millisecond delay on that interface. So in the topmost chart, we see static ECMP performs quite poorly. It takes around 4 seconds for the file to be transferred, whereas our adaptive routing has this nice characteristic where it's able to figure out one of the interfaces is performing poorly and instead redirect packets over the other interface. In the bottom left-hand corner, we have the BPF program overhead over time. That's typically somewhere between 400 and 1,000 nanoseconds. And in the bottom right, we show the NTP clock synchronization error also over time. And in some instances, this can actually get upwards of 1 millisecond. And for short-lived flows, that might actually become a major contributor to the overall error. One algorithmic consideration is by default, adaptive routing will redirect all of the packets in a flow if the latency becomes even infinitesimally worse. So we introduce a sticky hyperparameter to add an affinity for packets to stick to the same interface. So what we do is for this packet, we identify its 5-tuple flow. We look up to see what the previous interface index packets in this flow were routed over. And we slightly modify the condition from before to check if using this previous interface will still meet our deadline and that its current latency is within some sort of factor of the best possible. And on the bottom here, we show the interface selection over time for a TCP connection with varying values for sticky. So with sticky 0, it has this oscillatory behavior where there's 8 discontinuities in the graph. With sticky 1, it will always stick to the same interface. And the tuning problem is to figure out the best possible sticky value. With sticky 0.02, we see 2 discontinuities in our graph. One challenge we encountered is that we use wall time to compare NTP synchronized timestamps. And BPF provides a helper that gets us the boot time, but that is not synchronized. So what we're really looking for, and there is a proposed patch a couple of years ago as a BPF helper to get the wall time clock. Unfortunately, this was not merged upstream. So instead, what we do is we set an offset from the wall to the boot time, and we share that with the BPF program. We wanted to use a global variable for this, but since we load and attach with the TCBPF CLI, the user space doesn't have a reference to this global variable. So instead, we did it the old-fashioned way, and we stored it in a map with only a single element. Looking towards the future, we'd like to improve the scalability of our algorithm. We would like to support multiple hops on the journey from the source to the destination, and also support multiple priority levels, each with their own deadlines. Algorithmically, we would like to investigate a spread hyperparameter where we penalize redirecting different flows onto the same interface, because this creates contention, which degrades the performance of that interface. And finally, we would like to compare to other routing techniques, especially QoS. These are a couple adaptive routing references, and that concludes this talk. Thank you all for listening.
That was a neat one. Yeah, kind of reminds me. It makes me think a little bit about like the short-circuiting thing, where inside of app logic, if you're trying to connect to something that might be connected by multiple backends, you might determine the latency to that backend and maybe pick a different backend if that's not working for you. But at the TCP layer, like at the routing layer, that's mind-boggling. That's super cool. Really enjoyed that talk. So now we are going to go to a break, and when we come back, we're going to be joined by Liz Rice introducing the next block of talks, which instead of thinking about it from the networking perspective, we're thinking about what are we doing with all that context, the observability perspective. So we'll see you back at 10:20.
Welcome back to eBPF Summit 2024. I hope you had a good break. Maybe you spent the break having a look at the CTF challenges. I have heard rumors that there are people working on part 3. Post in Slack and let us know how you're getting on. We also earlier on talked a little bit about the bees that maybe you have around your house. I'm sure some of you saw in Slack this picture being posted. That is a lot of bees, Kurt. Thank you for posting that. If anybody else wants to post any pictures of any bees they have around them, please do go ahead. Another bee that I could show you is I have a little bee earring. So there we go. I've got a few secret stashes of bees here, so to keep you entertained. Right, more entertaining will be the next talk. As Duffy mentioned, we are going into a section of talks about using eBPF for observability, for visibility into systems. And our first talk in this section is from Tanil Poda, talking about tracking, not tracing, Linux thread activity for complete system visibility.
Hi, my name is Tanel Põder. Let's talk about Linux thread state tracking, not tracing. So every system provides utilization metrics, which is like the supply side. But I also want to see the full system activity from the demand side. And the demand is basically active threads doing stuff for you. And I want to be able to drill down into individual threads, like a log writer in a database. So can we do all of this without having to trace everything all the time? And yes. So I wrote a little tool set a long time ago, actually 2018 or something. But it blew up after I published a proof of concept prototype with BCC. And I will start from my old tool just to show you the concept, and then let's talk about eBPF. So my old tool, Process Snapper, just samples what proc files, whatever Linux kernel provides. I can sample, and I'll show you like a top activity. An activity is the time, wall clock time your threads spend doing something. It's not CPU utilization, it's not IO latency, whatever. It's the wall clock time of every thread of interest in your system, right? And whatever pops up near the top is what takes most of the time. So you could think of this data as like a fact table in a data warehouse. So this is really a count star of samples. I can derive how many threads on average were actually doing stuff then over the last 5 seconds or whatnot. And these are the dimension columns. It's essentially these are the columns you do a group by in the database world, right? And that allows you to look into the data from any angle of interest. Of course, here I'm limited with the proc file system only. With eBPF, you're not really limited by almost anything, because you can program and access any data you want, both in the kernel space and userland apps space with uprobes and then the USDTs and stuff like that. And that leads me to a little front-end tool what I wrote for the whole method and then the eBPF based data source. So I called it Desktop, and it's kind of the same. You see, most of the wall clock time has been spent by MySQL threads doing fsync system call, and by the way, these guys have not been on the CPU, or at least that state is not. Right, they are off CPU with this stack trace ID associated with this particular off CPU event. To show this, for example, there is some MySQL application connection thread who's doing an F data sync, also not on CPU, sleeping, waiting for something, and I have highlighted some of the stack IDs. And when you run this tool in command line, you'll just see an extra section. You see, here we go. So that stack ID is, you read it from here. Somebody ran the commit. That commit resulted in a bin log sync, and that resulted later on in an F data sync. And so how does this thing work, or the concept? So I mean, Linux has a task state array. Every thread you create will have to allocate the slot somewhere, and the slot has all kind of metadata about the scheduler state and so on, right? And so for now, I have created like a shadow array. That's the extended part, or really this is the extended part. And the shadow array is basically which contains all the extended extra custom metadata about what your thread is really doing. And not only in the Linux kernel scheduler level, but also in the application level. Like what system call is it in? What stack traces are associated by when it goes to sleep, or blocks and so on. That's only half of the story. So this extended task state array with all your custom extra context of interest, this is kind of between these two decoupled layers, right? So the eBPF programs that are attached to probes and trace points and so on, these are the ones which maintain this extra metadata for you. And then there is a separate layer that samples that metadata. So if you think about it like that, you have a thread that it's on, let's say it's on CPU in user space, and then it goes to sleep for some reason. Every time the state changes like that, perhaps this is still on CPU but in kernel mode, not user mode. Every time the thread state changes, we will update the extra extended areas of the task state array with the latest state only. We are overriding the state, as you see. You see, there is somebody runs many system calls per second. We are not somehow logging every system call into a trace that will be tracing, but we're just keeping the latest current state, additional state in this array. So, and that's where the second half comes into play. You can choose to sample this now. So this state, which always is up to date with all the extra context you want, you can sample this. By default, I sample once per second. First second you get this output. Next second you get this, right? And you may have 50,000 threads in your system, but you don't have to emit 50,000 threads information every single time, because you can define that, hey, the only interesting threads are the ones that are on CPU, trying to be on CPU, or are sleeping in the D state, right? And perhaps you can define whatever rules you want. So that's what tracking means, not tracing. We still get a reasonable overview of the entire system demand, not only utilization, but demand, but also you can zoom into a specific thread only if you want to, right? And you can have this always on mode as well, and it will create you a threads file for every hour for now, the active threads or the threads of interest, and for stack traces it creates a separate file. So if you want to go back in time to see what was going on at some point of time, then you can you maybe see that, hey, a lot of threads were waiting in this off CPU user mode stack, right? And now you go to the stacks file, you just grab for that, and you'll see what was going on. Why did this thread go to sleep back then? And there are awesome. I've only built like 5% of what I want to build, and there are some interesting things that might be possible, like for example, hooking into the scheduler a switch trace point, and whenever, let's say, the user application wakes up the database connection in a local machine, in this case, we can keep track of that. So this is not fully built out, but also this is from the same situation, right, or same time. I just highlighted a different thing. So there is this MySQL connection, and apparently at some point it has woken up the log flusher who did an fsync, and it has woken up even an ext4 file system journal writer and so on. So you could kind of plot out graphs once this thing is built properly. You can just see that if your commit is hung or the application is hung, you can maybe follow the path all the way to commit to log flusher, from log flusher to some sort of journal writer, And if latencies go up, or you even have a mini hang, this would show up in here. But I just wanted to show you, that there's some opportunities what you get once you start looking into every single thread, but not trace everything, which would be like too expensive. Okay, there are a lot of things that can be done, and many of the things are already, they're possible anyway because it's eBPF, and many of the things what I mentioned here are already implemented by other tools, right? Like extracting the distributed trace ID from the incoming requests. This could just become another column in the same extended task state array. Plenty of future plans. I want to build a V3 properly with modern eBPF. So if you actually have extra time, if you know how to do modern eBPF with all the things that I have in mind, and you have extra time, then please help out this open source project. And that's all. So try it out. Make sure you give feedback, and any questions are welcome. Just email me or get in touch online. Thank you very much.
That does look like a pretty cool open source project for eBPF enthusiasts to get involved with. So yeah, I encourage people to check that out. Thank you, Tanel. And there is a thread in Slack. So if you have questions about that project, then please go ahead and put those into Slack. So moving on to our next talk, which is a different take on, continuous profiling with OpenTelemetry. I'm delighted to welcome this next talk from Florian Lehner.
Hi, and welcome to Continuous Profiling with OpenTelemetry. My name is Florian, I'm a software engineer and member of the OpenTelemetry Profiling Special Interest Group. Continuous profiling is essential for optimizing application performance and resource utilization, leading to reduced energy consumption and a smaller environmental footprint. This talk will cover how eBPF enables continuous profiling of native languages as well as higher level languages without instrumentation. Earlier this year, Elastic donated its eBPF-based continuous profiling agent to OpenTelemetry. Now this code is licensed as Apache 2 and its code is available on GitHub for everyone. Due to eBPF, its footprint is quite minimal, meaning it introduces on average a CPU overhead of around 1% and requires roughly 250 megabytes of memory. The agent is capable of unwinding stacks without frame pointers. So applications do not need to be recompiled with special flags, and it is also not required to deploy debug symbols everywhere. At the moment, the agent is capable of unwinding stacks for native code like C, C++, Go, and Rust, as well as higher level languages like Java, Python, Ruby, PHP, JavaScript, Perl, and .NET. For AMD 64, the minimum required Linux kernel version is 4.19, and for ARM 64, it's 5.5. To get started with continuous profiling in your environment with this agent, no reconfiguration, instrumentation, or restarts of applications or services are required. Now let's talk about how this profiling agent utilizes eBPF to make this possible. Most important to know, the profiling agent takes advantage of the perf subsystem of the Linux kernel. The perf subsystem provides performance analysis capabilities within the Linux kernel with detailed information about various hardware and software events, as well as system-wide performance metrics. The profiling agent uses a technique that can be described as lazy loading, which is shown in this diagram. Every 50 milliseconds, an eBPF program is called. This program then checks if the process to unwind is known or new. If the process is known, the eBPF program will do a tail call to continue stack unwinding. If the process is not known at this moment, the eBPF program will inform the user space via the perf event array map. The user space component then makes sure to populate eBPF maps with information about this process, so that at the next iteration the eBPF programs can unwind its stack. This technique allows a simple workflow as it does not require eBPF programs to be attached and managed on multiple other process-related events in the Linux kernel like fork. On newer Linux kernels, eBPF helpers like BPF find VMA are available to fetch the backing memory mapping for a process, without requiring the user space component to resolve it. But this helper is only available for Linux kernels newer than 5.17. The profiling agent uses LPM eBPF maps to make memory mappings within a process available to the unbinding eBPF programs. LPM maps are most well known in the networking space for filtering or routing topics. The struct BPF LPM tree key shows an example of such a use case. The LPM map key for the profiling agent looks a bit different. The process ID as well as the memory address of a memory mapping within the process is encoded within the key of the LPM map. Memory mappings within a process are usually aligned to some extent, and so the LPM map provides a convenient way to organize them. A dummy entry for known processes also allows the eBPF programs to check this LPM map if the process is known or the user space component should be informed, as seen on the previous slides. But how does the profiling agent gather information to be able to unwind the stack? On modern Linux kernels, eBPF helper functions like BPF getStack are available, as well as BPF task ptrex. While the eBPF helper BPF getStack would be available for the minimum supported Linux kernel version, the profiling agent gathers required stack information a bit differently. Also, the minimum supported Linux kernel version was just recently increased from 4.15 to 4.19. For this reason, there are two steps involved in how the profiling agent fetches the required information to be able to unwind the stack. The first step happens once at startup. Memory of the struct task struct is inspected for the offset of the field stack. The value of this offset is then placed in an eBPF map, here called systemconfig, to make it available for eBPF programs. The eBPF map systemconfig is used to communicate configuration options from user space to the eBPF programs, as BTF is not available. The second step happens every time eBPF programs unwind the stack for a process. With the offset from the eBPF map systemconfig and the return value of BPF getCurrentTask, a function can get the necessary information for unwinding the stack. Fetching the registers is an important step, as some higher level languages use some registers to store additional information for their interpreter virtual machine. This concludes the short introduction into the OpenTelemetry profiling agent. Thank you for your attention and happy profiling.
Thank you, Florian, for that great talk. And if there's another thread in Slack, so if you have questions for Florian, please add them into that thread. And also, just show your appreciation with a little applause emoji. That would be really nice. Moving on, our next talk is from Vamsi Kalapala and Anubhav Majumdar, and they are going to be talking about enhancing efficiency and visibility, optimizing eBPF programs for advanced observability.
Good day, everyone. Thank you for joining us today at the eBPF Summit 2024. My name is Vamsi Kalapala, and I'm joined by my colleague, Anubhav Majumdar. We are excited to share our insights on enhancing efficiency and visibility, optimizing eBPF programs for advanced observability. This session will delve into how we can design more efficient and scalable eBPF programs for network traffic observability. To give you a brief overview of what we will be covering today, we will start with an introduction to the problem space and provide some context around network observability challenges in Kubernetes environments. We will then discuss potential solutions. Let's begin with a bit of background. Our work is part of the Microsoft Retina project, an open source eBPF-based Kubernetes network observability platform. Retina is a lightweight solution designed for continuous monitoring. Traditional monitoring solutions often struggle to keep up with the dynamic nature and volume of network traffic in Kubernetes clusters. This is where eBPF comes in, offering a powerful way to monitor network traffic at a granular level. As we dive deep into the problem, it becomes evident that continuous network monitoring in Kubernetes clusters is no easy task. The first challenge is event volume. In a large-scale cluster, the amount of network traffic is immense, and observing every packet can quickly become overwhelming. This leads to the issue of resource footprint. How can we monitor such a high volume of events without consuming excessive computational resources? Another critical challenge is data accuracy. In an environment where thousands of events are generated every second, ensuring that the information collected is accurate and actionable is paramount. Lastly, there's the overhead on data path latency on customer workloads. eBPF programs, while powerful, can introduce significant latency, particularly when they are not optimized. This added latency overall performance of the network, which is something we must carefully manage. The challenge here is to achieve accurate network event information at scale without sacrificing performance and efficiency. So given the challenges we have just outlined, the key question is, how can we optimize network observability in Kubernetes clusters without overwhelming our resources? First, we need to critically assess whether we truly need to capture all the events. Often the answer is no. Capturing every single event can lead to excessive cost, resource consumption without delivering proportional benefits. Instead, we should focus on event relevance, prioritizing events that would provide actionable insights and disregard the rest. Another important consideration is the application context. Users generally care about monitoring specific namespaces and pods rather than the entire cluster. Not all packets are equally important, and the key is to identify which ones are critical to the user's needs. Furthermore, it's crucial to ask, can we selectively monitor only the pods that are of interest to the users? By doing so, we can significantly reduce the volume of data we process, making our eBPF programs more efficient while still delivering the visibility required. With that, I'll pass it over to Anubhav, who will talk you through the specific solutions we have developed to tackle these issues.
Thank you, Vamsi. The first solution we implemented is pretty rudimentary. We allow users to annotate namespaces and/or pods that are of interest to them and record the IPs of those pods in an eBPF map. The eBPF program is modified to match the source and destination IP of each packet it sees against the map to determine if the packet is of interest to the user. If you're interested in only a small subset of pods, this solution works great. But the disadvantage is it doesn't provide monitoring of the entire cluster, which is one of the most potent features of continuous monitoring. Moreover, if user annotates all namespaces, it negates all advantage this approach provides. The second solution that we implemented is based on the principle that not all packets flowing through a node are equally important. Rather, a small subset of them provide actual useful signal. For example, in a long-running TCP UDP or UDP connection, user cares about when the connection is established and how long the connection is alive. They do not care about signals for every data or acknowledgement packets flowing through the node as part of the connection. This allows us to sample packets rather than reporting every packet encountered by the eBPF program. This slide provides a very simplified version of the algorithm we use to determine the packets of importance. To do this, we maintain a list of recently seen unique source destination IP port pair. For every packet, we check against the list to see if the connection is new. If yes, we report it immediately. Otherwise, we only report data or acknowledgement packets every 30 seconds. The list is curtailed when we encounter a finish flag or after a certain amount of time. The big advantage that we can provide is we can provide continuous monitoring for all pods in the cluster and not a subset of them. This also reduces the network latency because we write very small number of events to the perf array, and that is the most costly operation that adds to network latency. One downside of sampling is if we want to accurately measure the amount of bytes a pod receives or a pod sends, and we want to do this calculation in the user space, we cannot do that anymore because we are sampling at a kernel level. So how much does this enhancement that we discussed improve performance? This slide shows the advantage of sampling when reducing missed events from kernel. To create a baseline, we set up a cluster running ping mesh pods, installed Retina without filter map or sampling enabled, and ran it for 30 minutes. During this period, we counted the number of events that got overwritten in the perf array because the user space program couldn't read them fast enough. The light blue line shows the result. In the same cluster, running the same number of pods, when Retina is installed with sampling enabled, we can filter out almost 90% of packets seen in the node without missing any new connection established by a pod in the node or to a pod in the node. Sampling can even outperform filter map-based approach, where we observe only a third of the pods running in the cluster. Similar benefits can be seen when measuring network latency introduced by eBPF programs. We used iPerf and NetPerf tools to measure throughput and mean network latency respectively for both intra and inter-node traffic. Baseline is established on a Kubernetes cluster without Retina installed. The graph on the left shows transaction rate, while the graph on the right shows TCP round-trip latency. To establish the worst performance, we installed Retina without any of the enhancements discussed. We impact throughput and latency quite significantly. For example, Retina without any improvement can add almost 10 microseconds to mean latency in intranode pod-to-pod TCP communication. Next, we installed Retina on the same cluster with sampling enabled. By leveraging sampling, Retina introduces slight to no latency in both throughput and TCP round-trip time. For example, Retina introduces only a 2 microseconds to mean latency in intranode pod-to-pod TCP communication. In conclusion, we saw that by using sampling in eBPF programs, we can provide key metrics continuously without sacrificing performance or breaking the bank. Some enhancements that we want to make in future iteration of Retina is to provide an accurate measure of bytes each pod receives or sends, or the total amount of bytes flowing through a node. Allow eBPF programs to behave differently to adapt to change in traffic pattern, and allow users advanced control over eBPF program behavior to fit their own use cases. That concludes our presentation. Thank you so much for listening to us. Thank you.
Thank you, Vamsi and Anubhav. I thought it was really interesting to see how reducing the number of events that you're collecting in the kernel and thus making fewer events have to be passed to user space makes things so much more efficient and reduces that overhead. We're taking a sort of similar approach in Tetragon as well, filtering events in kernel. And yeah, it makes a huge difference to the amount of information you can collect, but with a really small amount of overhead. So if you have questions about that talk, as always, please put them into the Slack channel, and I'm sure Vamsi and Anubhav will be delighted to answer them. Moving on to the next talk, our next speaker has actually been a guest with me on the Echo live stream before, talking about the BPF Time project. Please welcome Yusheng Zheng, who's going to be talking about BPF Time, user space eBPF runtime for network and observability.
I'm Yushan Zheng. I'm from Eunomia BPF. I'm excited to talk about BPF time, a use-based eBPF runtime for network and observability. You may remember BPF time from last year's Linux Plumber, but we've made a lot of progress since then. So what's BPF time? It's a use-based eBPF runtime that supports tracing features like uprob and USTD and Cisco trace points, and even network features like FTP or in use-based. It can support more than 10 types of maps and 30 types of helpers, so it's highly compatible with kernel eBPF ecosystem. And you can also use your familiar way to develop and deploy eBPF programs in use-based. eBPF can run alongside with BPF can run alongside with kernel eBPF using kernel eBPF maps and working together with kernel eBPF events like kprop. It can now using error uBPF, which is already used by eBPF for Windows, or a new eBPF virtual machine called LVM BPF as its virtual machine for execution. You can find a link to BPF time here. So why do we want to do observability with eBPF in use-based? It's simple. Use-based tracing can be faster and more flexible. For example, uprops in kernel takes about 1,000 nanoseconds, but in use-based, we roll that down to about 100 nanoseconds. Similarly, memory access in use-based is about 4 nanoseconds and about 40 nanoseconds in kernel. This space speed difference happens because the kernel often has to translate memory address or run some additional checks to access use-based memory. On top of that, there's less overhead on untraced process, especially when dealing with Cisco trace points. So, and also, what can be run in use-based with use-based tracing? Tools like BCC and BPF trace can run completely in use-based where kernel eBPF is not available, like all version or unprivileged containers. And you can run more complex observability agents that can combine kprops and uprops, improving performance by shifting part of the workload to use-based. Now let's talk about BPF time in the network context. Why we can use use-based eBPF instead of running eBPF in kernel? Within kernel bypass solutions like DPDK and AFXDP, they can offer faster packet processing by bypassing the kernel, but with BPF time, you can combine the performance benefit of these kernel bypass technologies with the extensive eBPF ecosystem, so you get the best of both, like low latency packet processing and ability to use eBPF safety and existing eco tools. We can also use LLVM optimizations to further improve the performance in use-based. Why we need BPF time? We already have eBPF with DPDK support, but the DPDK support has no eBPF maps and helper supports. There's no control plane application with the eBPF for DPK, and we can use the faster and more optimization with LLVM. Use BPF time, you can seamlessly integrate the eBPF SDP ecosystem into kernel bypass application. For instance, solution like Catron, a high-performance load balancer, can benefit from the optimization we've made in BPF time for use space. You can also run your SDP eBPF programs as if they were in kernel. Just load them with BPF time, and they will work like normal kernel eBPF programs, where you can start another DPDK application handling the network process. BPF time can work with both AFXDP and DPK. Right now, there's some limitations with BPF time network in use space because we only support ADP tier and ADP drop. We are actively working on solutions and exploring ways like to re-inject packets into a kernel to support ADP paths. One of the core features that allow BPF time to remain compatible with existing eBPF ecosystem is its control plane support for use-based eBPF. Control plane in eBPF are usually responsible for tasks like loading and unloading program, configuring maps, and provide monitoring and debug interfaces. BPF can support this in use space by hooking syscalls using LD preload or kernel eBPF modules, and we can connect the control plane application to the use space eBPF runtime with shared memory maps or shared memory controls. Now let's see the performance benchmarks. We can see there's AFXDP deployment and DPK deployment. In use space, we can compare them with ADP in kernel. We've benchmarked a variety of eBPF programs running with BPF time. BPF time can achieve up to 3 times faster performance in simple ADP network functions. And in real-world applications like Katra, BPF time can achieve up to 40% faster. The link is below for the experiment. This shows that use-based eBPF can be faster with kernel bypass solutions while retaining the flexibility that makes eBPF powerful. And originally, LVM BPF was part of the BPF time report, but we've now separated into a standalone project. LVM BPF is a vBPF virtual machine and compiler tool specifically optimized for use space. We've tested with BPF conformance with compatibility, and you can see that in CI. It can have better performance, and we can easily experiment different optimizations such as inline helpers. The LVM BPF also supports both skip and help time compilation, depends on what you need. It's an easy-to-use library, like the eBPF. LVM BPF also supports we can build eBPF programs into a standalone binaries where you can call the eBPF modules like a simple C code and use the eBPF bytecode here as the IR for verification. And maps and helpers are also supported in these cases. In these cases, you can make it very easy to deployment because you don't need any external dependencies. This can make it easier to deploy eBPF programs on any machine, including embedded systems and microcontrollers, which often don't have the OS or runtime support for eBPF. In conclusion, BPF time are more than just a use-based tracing and network framework. We hope it can bring the power of eBPF ecosystem into use space without compromising speed or flexibility. I recommend all of you to explore BPF time for your tracing and network needs. And also special thanks for Professor Merrill from Imperial College London, and thanks for your time. Feel free to check out the reports on GitHub or ask me any questions.
Thank you, Yusheng. I think it's really interesting to think about the use cases for BPF in user space, and some of those use cases, like being able to run BPF in sort of to monitor user space applications and not having to transition to kernel space, and also that ability to run BPF programs without needing kernel privileges. I think that's very interesting. So if you have other use cases for BPF time, I think it would be really interesting to hear about them in the Slack chat. We are about to go for another break. Before we do, I just want to give a little thanks and round of applause to the program committee for the eBPF Summit. We had 17 people who helped us out with reviewing the talks that you're seeing today. So very much appreciate the time and effort that people put into reviewing all the talk submissions. So yeah, thanks to all those people. We're going to take a quick break and we will be back at 10 past the hour for the next series of talks.
Awesome. Hope you all enjoyed that break. There's been, as we said, some great work happening on the CTF. And this next set of talks introduces some of my favorite stuff, things like chaos and security and things like that. So our very first talk of this next section is going to be brought to us by Scott Gehring, talking about break all the things eBPF as an agent of chaos.
Hi, I'm Scott, and today we're going to look at how eBPF represents a new way of approaching chaos engineering by shifting some of its capabilities left in the development lifecycle. Chaos engineering was pioneered by Apple in the 80s, and I would say popularized more recently by Netflix's Simian Army. It lets us experiment on a running system in order to build confidence it will effectively tolerate failures. This means so far coarse-grained destruction of virtual machines and cutting networking off at different levels of granularity. We can do this sort of thing cloud style, so in AWS, as Netflix famously does. We can also do it using something like Chaos Mesh in Kubernetes, which in some cases is already using eBPF, which is cool to see. It lets us at a high level catch two classes of errors. One is the emergent behavior of all of the services, all of the components in my system is such that it fails in a poor fashion when we introduce this class of error. The other is this particular service, service 1, fails when we introduce this class of error, or rather fails in a way that isn't optimal. This stuff is great, especially for complex failures across multiple services. But on the other hand, it shouldn't really take an entire cloud environment to discover that service A is failing in a poor fashion when the network around it breaks, by way of example. The earlier we can catch these errors in the software development lifecycle, the easier and cheaper it's going to be to fix them because we're closer to the change that introduced them. Here as an industry, we've lent on component testing historically. It's somewhere in the middle of the testing pyramid, and the idea is that we spin up a service in isolation and stub remote service calls out. This also gives us a chance to introduce failures into those stubs and see what the thing does when those failures pop up. This is good practice, but tends to be quite cumbersome to code, particularly for failure cases, because we have to write a lot of stubs. If we have lots of downstream services, it's that many stubs, and then times the different number of failures we want to introduce, which means that we probably do this less than we could because of the friction involved in doing it. With eBPF, on the other hand, we have this universal language of destruction. We can go and inject the same sort of failures without having to extensively modify the code of the service under test, instead wrapping the whole thing up with some tooling that says, within the bounds of this call, break all network IO that looks like X, this port, that sort of thing. This can be done generically with regards to the language of the service because we're doing it out of process with eBPF. And we also have the power to do it using the same tools regardless of failure mode, because eBPF lets us introduce failures in the network path and the kernel interface and the security module interface, all sorts of different things, but always with the eBPF tooling. So let's have a bit of a look concretely at how we can break things. Here we have a kprobe attached to the OpenAT system call that's returning access denied for 50% of invocations made by targeted processes, where the targeted processes are passed in as a PID list in a map from user space. We use BPF override return to short circuit the system call and return an error back to user space, essentially making OpenAT fail in a controlled way. This example is written concretely for OpenAT, but because the system call interface is fairly regular in terms of how system calls are invoked and how error numbers are returned back to user space, we could also generify this up pretty well so that we have one set of probes that we use to fail all sorts of different system calls. In this example, we're using the traffic control subsystem and its filters to randomly drop traffic for targeted processes in the outgoing direction. First, we hook socket creation. If the socket's for a targeted process, we set a mark on the socket's SK buff, and we can then pick this mark up later on in the TC filter. We use TC act stolen to drop the traffic. This is a nice one for our purposes because it indicates to the caller that the traffic got through the packet pipeline successfully, so it looks the same as network packet loss happening outside of the machine. And we get that without having to pull cables out of switches and without having to have a full-blown cloud environment. So far this is really just a nice idea and a tech demo. I would love to see this sort of thing built into test frameworks with some common Golang eBPF backend and a bit of a UI bound into, say, JUnit, GoTest, what have you. It would be nice to extend it to use other potential probe points within the kernel. The express data path, for instance, seems like a natural fit for introducing coarse-grained network failures. And the LSM could be a good way of introducing security failures. It would also be nice to see other less absolute failure modes. This means resource exhaustion, for instance, potentially by tweaking cgroup limits. The experiments I've written so far and code from the slides is available on my GitHub. It's very incomplete, but you can run it and use it. Feedback and ideas encouraged. Thanks for listening and enjoy the rest of the sessions.
This type of chaos engineering is so important, like it's one of those things where if you're asking yourself, what would happen if this happened? I think you're on the right track, right? And then the question is, how can you make that happen in your environment so you can learn what happens when that happens? And that stuff just is super exciting to me. Thank you, Scott, for that amazing talk. There is a thread in Slack where you can interact with Scott, asking questions and that sort of stuff. Our next talk is from B10C, talking about monitoring Bitcoin P2P network attacks and anomalies with eBPF and USDT trace points.
Monitoring Bitcoin P2P network attacks and anomalies with eBPF and USDT trace points. Hi, I'm ZivXBTC and I contribute full-time to open source Bitcoin projects. One of these projects is Bitcoin Core, the most widely used implementation of the Bitcoin protocol. The software powers the network with a market cap of more than $1 trillion. This is roughly equal to the market cap of Meta. Bitcoin Core development has a strong focus on security and doing proper software engineering, as problems can hurt the network and bugs can cause users to lose their money. This includes extensive review of pull requests, good unit, functional and fast test coverage, along with test networks and simulation tools. But this doesn't reduce the need for monitoring of development builds, release candidates, and production deployments. The most important part to monitor is the P2P networking functionality. The Bitcoin P2P network is a distributed system consisting of tens of thousands of nodes, gossiping transactions, blocks, and IP addresses of other nodes. As the network is open and everybody, good or bad, can connect to the nodes, monitoring the behavior of the software in a potentially adversarial context is important. Attacks we are looking for are, for example, denial of service attacks, which either take up system resources or in the worst case crash the node, as well as privacy attacks or Eclipse attacks. Motivated by anomalies previously only observed by coincidence, we spun up a few honeypot nodes. These nodes run different software versions, development builds, pre-releases, releases, and all have different configurations applied. The goals here are twofold. First, being able to analyze attacks, anomalies, bugs when they happen, and secondly, being able to feed the data, insights, and learnings back into development. To look into the software behavior during runtime, I've opted for tracing with eBPF and static trace points. Static trace points, compared to dynamic tracing with, for example, uprobes, allows us to have a semi-stable API even if the code is being refactored across versions. There are, for example, trace points for opened, closed, and evicted connections, as well as for inbound and outbound messages. These are implemented using the system tab probe macros. The trace point interface is tested in the CI with the Python frontend for BCC, and there are BPF trace and BCC example tracing scripts. The snippet shows the trace point for inbound P2P messages. 6 arguments are passed to the trace point with information about the peer which sent the message and the information on the message and the default message payload. The actual eBPF code for the monitoring lives outside of the Bitcoin Core project, the P-Observer project. Specifically, the extractor tool written in Rust uses libpf rs to interact with eBPF. The eBPF program is written in C, and the eBPF cargo is used to generate the Rust bindings for the functions and maps in the eBPF program. The t-structs that we pass around are read with the read underline function from the Rust standard library into the Rust struct counterpart. All right, as an example of how this works, in user space, the Bitcoin Core node receives an inbound P2P message from a peer, and the message is processed in the process messages function. In this function, there's also the inbound message trace point. The trace point is reached, and the trace point arguments contain the information about the peer and the message we received. The function handle net message inbound from our eBPF program is hooked up to the inbound message trace point. This means once the trace point is reached, the function is called in the eBPF virtual machine in kernel space, and the trace point arguments are passed into this function. We reserve a P2P message struct in the ring buffer and fill in the trace point arguments. Using reserve submit here has the neat side effect that our struct is not on the eBPF virtual machine stack, but already on the ring buffer, and thus can be larger than the 512 byte stack size limit of the virtual machine. The payloads of Bitcoin P2P messages that we pass along with the trace points and want to have in user space are frequently larger than the 512 byte stack size. Once a struct is submitted to the ring buffer, the last two steps happen in user space again. The extractor reads the C struct from the ring buffer and converts it into a Rust struct. The Rust struct is then forwarded to our tooling and is, for example, used to generate metrics and in our anomaly detection. This allows us, for example, to visualize the messages being exchanged between a node and its peers in real time, which is a good demonstration showing the throughput of the tracing. At the same time, we can also derive time series metrics from the events and show them in Grafana dashboards. Some of these metrics are used for anomaly detection and automatic alerting. To wrap up, here are my closing thoughts on tracing Bitcoin Core with eBPF and USDT trace points. The combination of eBPF and trace points certainly fulfills the requirements for a real-time stream of events from Bitcoin Core. It gives us detailed insights into what was previously mostly hidden in a black box, and it's good to have a machine-to-machine interface as compared to logging, for example, which is more a human-to-machine interface. For our implementation, we made sure that preparing the trace point argument isn't expensive, like serialization or hashing, and we don't place them in tight loops. Similar for gating the trace points, that means only preparing the trace point arguments when someone is actually hooking into them eliminates all runtime overhead when nobody is using them. We have an open pull request for this. The eBPF side and the ring buffer seem to be quite performant for our use case. Inserting new trace points has a minimal code signature of only adding a few lines consisting of the trace point macro. Most of the code added along with trace points are the interface tests for them. One obvious limitation is that our eBPF tooling only works in Linux, and we can't use it to monitor on macOS or Windows. I have experimented with reusing our tracepoint macros for dtrace probes on macOS and FreeBSD. This would allow tracing on these platforms too. We've also faced problems with testing the tracepoints in CI. This ranges from problems with the Ubuntu BCC package not being up to date or broken, to our CI running in containers which might have a different kernel from the host system, which led to problems. And looking at the process in general, extracting events from a user space C++ process via an eBPF program in a kernel written in C to a user space program in Rust or Python could be seen as a detour via the kernel, especially with the permissions required for BPF syscalls. Advising people to run random tracing scripts downloaded from the internet as root might also not be the best idea. All in all, eBPF and USDT trace points gets the job done. Well done, I would say. But it might require you to jump through a few hoops on the way there. Alright, thanks for joining. I will be around in the Slack channel for the Q&A.
That was a neat one. Awesome stuff, kind of talking about how to monitor Bitcoin and that sort of thing. BTNC is in the chat. We have a thread going on. Feel free to ask any questions that you have. Our next speaker is going to be Reinhard Kugler talking about living on the edge, securing containers on embedded platforms using eBPF.
The device edge and the cyber-physical system is in transition right now. And what we're seeing is that cloud technologies now come down to earth, and we can observe how it's changing different domains which are usually quite static. So what we are seeing right now is that in automotive and in production systems, the pace of cloud to integrate cloud technologies is quite high because they need to update and remotely configure their systems more and more, and don't have the personnel to that the person goes to the system or to the car and change it all of it by hand. So what we are seeing, for example, in the automotive world is the centralization of software from these metal boxes on the left top corner, which is usually the electronic control unit hosting different software components like your seat heating, your reverse camera, your automatic steering, and some of the functions are centralized in one place, the high performance computer, which is usually just an ARM platform hosting Linux processes and virtual machines in parallel. So this is quite a change in a system like this, and cloud technologies also come into play. Therefore, the cloud providers jump the wagon and try to provide in-vehicle operating systems for this domain. So those are Linux systems that should be safety certified and run in cars nowadays. I would like to focus on one attack we saw some years ago, the famous cheap hack. If you don't know it, it's more or less the blueprint for every cyber assessment in this domain. And what they did is they attacked a car via the internet, found a service that it was exposed by IP and port, and therefore they found a way into their infotainment system of a car. And in the end, they took over this infotainment system, also changed a chip. So they overwrote a chip inside this infotainment systems to gain access to the overall vehicle network. So there, the information is flowing back and forth to steer your car, to change gear, to change the lights, and so on. And therefore, they were able to fully control the vehicle. So there are two areas we want to focus our attention, and one is the internal bus systems that are used to, for example, overwrite and update and patch systems inside the whole PCB, the printed circuit board, so your hardware. And the second part is the injection of messages into this vehicle network. And all we want to do is to do this with eBPF, because we already have containers, we already have Linux, and therefore, how can we influence it? And to get an understanding of this in-vehicle network, it's a big network of many components, and therefore you need to have a way to communicate, and that's the CAN bus. It's just like IP, but a different way, right? It's a different protocol and different electrical way to transmit information, which has some safety considerations and priority in mind. But for us to break it down, we just have an ID, what we transmit, and the data, and that's what we're working with. Of course, there's more to it, but from a starting point, we can use this, and in the Linux system, it's represented already as interface. So you will have a CAN 0 interface, like your Ethernet 0 interface, if you use CAN and a CAN driver. So every time a process wants to write to this bus, there is already a socket implementation for that. So you can write to this CAN 0 interface, and this is then routed to the driver, and the driver talks to the CAN transceiver, so the hardware that's actually forming the signals on the bus. And in the end, you have an electrical signal that's interpreted by your car and, for example, opens the door or starts the engine or changes the lights or steers the car. So how can we, for example, prevent injection attacks? We saw usually a bus is quite hard to protect. So if we focus on a container with a specific software, we could add to the network stack an eBPF program. So we attach it at a specific point. For example, here we attach it in the processing of this information in the XDP hook. So we hook it, and every time a packet gets received, it's calling the program for that. And therefore, we can write the behavior. To show this as example here, you see that the CAN bus on the left is transmitting information. You see all the different messages and IDs back and forth. And as you load the program, this eBPF program, the bus goes silent. And in this very simple implementation, you can change by a map the way how this program works. So in this case, we let it all through. And if we want, for example, to limit the length, we also have an operation mode for that. So every time we get the packet, we inspect it for length, or in this case, we inspect it for a specific value to be present, for example, as a format or a value constraint, or even something more complex like signatures. Of course, in the end, you can make it get it back to normal. You can let it all through or block it all. And you can also see in the background here, the packets still get received, but are blocked by this program. So to sum it all up, if we find a way to block this, we can also influence how the network is accessed. How can we also prevent overrides of this flashing? And usually flashing in IoT systems are used by the SPI bus, which usually talks to a flash chip, right? And you don't have to know everything about it, but in the end, you have, for example, in the Linux system, a SPI-def device, which represents how to talk to this chip and to address, for example, exactly that chip to override it. And the Linux kernel takes care of, okay, how this signaling is done in the background. So we can again add a eBPF program for that. We can say, okay, maybe we block it as you get a specific CAN bus, specific SPI ID. So in this example, we quickly show that the SPI bus is used to override a flash. And on the right, we have this logic analyzer hooked up to see the actual signals. And as we use the eBPF program again to block this device, we go a bit forward to load the program. And as it gets loaded, boom, all the bus goes silent because it's not allowed to overwrite. So what can we learn from that? What is the cloud technology for the cyber-physical systems? It's how we can build defenses around, for example, third-party contributions or third-party software. And that's really helpful to create observability and security boundaries without touching the application or to change the application for this ever-changing threat landscape. So thank you for your attention. If you want to need more, please get in touch with me. I'm happy to discuss, and thank you for your attention.
And we do have live in the chat answering people's questions and interacting. And I completely agree with that statement about the ever-changing threat landscape. I mean, like with electric cars and all of these things starting to become even more prevalent, and CAN bus systems kind of just starting to like get significantly more complex, it's really neat to see the type of work like this kind of really focusing on the security of those things so we can be safe when we're out there driving. We are going to go to another break, and we're going to come back at 45 after, where we are going to bring Liz back to introduce the next block of talks. Have a quick break. See you soon.
we are back here at eBPF Summit 2024. I promised you some more bees. These are probably my smallest bees in this lovely little Lego beekeeper. Right, I think it's time to move on to our next talk. This is by our friends at Control Plane, James Callahan and Jack Kelly, and they're talking about demystifying eBPF security, navigating risks, safeguards, and best practices.
Hello, and welcome to our talk, Demystifying eBPF Security, Navigating Risks, Safeguards, and Best Practices. I'm James Callahan, a Principal Consultant at Control Plane, a cloud-native security consultancy. I work as a security architect and have been involved in the past with the creation of several open-source threat models, including those for Envoy Gateway and Argo CD. I'm here with my colleague Jack.
Hello, I'm Jack, also for Control Plane. I'm a senior consultant with a strong focus on engineering and a love for security. I've done threat modeling work in open source in the past. I'm sitting on the Intoto steering committee, and I package a few eBPF tools for NICs.
So our talk today is going to be based on an eBPF threat model that was recently commissioned by the eBPF Foundation. The goals of this threat model are ultimately to help large organizations to adopt eBPF tooling safely and securely. We want to explore what an attacker could potentially do with eBPF. We want to detail eBPF safeguards that are in place that will actually reduce these risks. And then we also want to provide recommendations on the secure use of eBPF tooling generally beyond the inbuilt safeguards. A really important thing is that threat modeling is collaborative. We will refer out to some really excellent work in the threat model paper itself. And then also we have relied on input from some true eBPF experts. So thank you to absolutely everyone who has helped us in the creation of this threat model. We're going to be following the show stack 4 question framework when we are doing our threat modeling. First of all, we need to ask, what are we building? Ordinarily, this step would involve going into low-level detail about a system. However, we are considering eBPF generally, rather than a specific implementation. Therefore, we've kept the scope extremely high, which we'll see on the next slide. Once we have a scope, we can start catastrophizing and asking the question, what can go wrong? We will use attack trees to enumerate what steps an attacker would have to take in order to achieve a high-level goal, which will ultimately always revolve around compromising confidentiality, integrity, or availability of business data. Once we have done this brainstorming, we can collate the threats into a final set and devise mitigating controls by asking, what can we do about it? As we said before, eBPF helps us here with inherent safeguards that we will discuss, but also we will consider best practices which could apply to eBPF tools or otherwise in order to supplement these inherent controls. The final step considers whether we have done a good job, and this can be answered, for example, by looking at our attack trees, mapping controls, and ensuring that we have full coverage. So here is our scope. In order to derive the most general set of end user recommendations, we will make a few assumptions. First of all, we will have user space workloads running in a multi-tenant platform where different tenants' workloads could possibly be co-located on the same Linux host. We will not make any assumptions, however, about how these workloads are orchestrated. Another assumption we'll make, you can see on the right-hand side, we have a platform team running eBPF programs for observability, networking, and or security reasons. Again, we're going to be very high level and not very specific here. And then finally, we will not make any assumptions about the security context of tenant workloads. So in the worst case, where workloads could run with elevated privileges, for example, malicious tenants could attempt to run eBPF programs that they shouldn't in order to bypass security control. So here is an attack tree example, which Jack is going to walk you through.
So yeah, we're going to take a look at an attack tree. We're only going to look at one, and more specifically just part of an attack tree, just due to the time we have. Important things before we get into it is what is the legend we're using. So we have leaf nodes, we have and nodes in blue, which means we'll need both of the items below, and all nodes in green, so either option works. We're going to go top to bottom from the attacker goal, in this case, unauthorized access to sensitive information, and yeah, we'll go from there. So at the top, we got the goal, as I just mentioned, and we're going to take the left path. So we're a co-tenant on the machine, and we want to look at files that we shouldn't usually have access to. So in order to do this, we got a blue node. So we need both of the options below. We are assuming we're an internal platform user, and that could be either of those options below, either an admin or, in this case, I think it's most interesting to look at a tenant that's been given the ability to run eBPF. So that's kind of our actor in this case. And on the other side, we've got the helper function that we plan to use. So this node is an AND, so we'll want both of these paths. In this case, we're going to need certain capabilities. So if we have cap sysadmin, we can use this helper function. And then in kernels 5.8 and onwards, there are more granular capabilities for this. So we could have cap BPF plus cap perfmon. So either sets of those capabilities would allow us to use this function. And then on the left, once a user that has access to that file opens the file, we would then get to read what they saw.
Okay, so now we've been through one branch through an attack tree, we can start to think about what controls can prevent some of the bad things that can happen. Now, first of all, we'll go through the inbuilt eBPF controls, the inherent controls, if you will. The first of these is the verifier. So before a program can be attached to an appropriate hook, the eBPF program must pass through the verifier, which carries out a few checks. It confirms that the process loading the eBPF program holds the required privileges. It confirms that the program does not crash or otherwise harm the system. And it confirms that the program always runs to completion and doesn't, for example, just sit in an infinite loop. It does these things and many more, but this is kind of the first safeguard that we'll come across. It's worth saying a little bit more about privileges, because as Jack showed in the attack tree, that attack path could not have been carried out if the tenant could only run a program with cap BPF and cap netadmin, for example. So this is quite a good inherent control that we can build on when we design the kind of least privilege model, which Jack will go into on the next slide. Finally, there's a bunch of these which we'll go through in the paper, but we'll just draw out another one here, which is that warnings are printed to kernel logs if an eBPF program tries to do something particularly nasty, such as writing to memory associated with some arbitrary process. So these are the inbuilt controls, but we also have some recommendations that we make, which Jack will take you through now.
So yeah, this is a non-exhaustive list, but just a couple to give you a taste. We've covered kind of more granular capabilities, but also if you make sure that your processes loading eBPF aren't too exposed, that leaves you less options for attack. We've got separation of duties, so this is recommending that loading eBPF programs is probably a system administrator type action for these multi-tenant machines. And then, as with any program, supply chain kind of best practices are always good. You want to have increased confidence that the program is from the right people, the right vendors. If it's open source, you can take a look at what the program's doing, that kind of stuff. If you're loading your eBPF from a process that you're running in a container, then you've got a nice option for applying signing if you make sure that image is signed. But yeah, thank you so much for listening.
Thank you to James and Jack. If you would like to receive a copy of that threat model white paper when it's published by the eBPF Foundation, there is a link that you can sign up to get that notification. I've put the QR code up there and it's also in the Slack channel. So that'll be a good way to get hold of that white paper when it is completed. I also want to congratulate James on the best use of the verb catastrophizing that we've seen so far in eBPF Summit. Backstage, we've all been very impressed by that word. What we're going to be impressed by next is our next speaker, who Alan Maguire has been a repeat speaker on eBPF Summit. He always has some really interesting kind of in-depth insights into eBPF. So please welcome Alan Maguire, who's going to be speaking today about BySysCall, exploring how to use eBPF to bypass system calls.
Hi, my name is Alan Maguire, and I'm here to talk about BySysCall, bypassing system calls using eBPF. So system calls represent the interface between user space programs and the kernel. It's when we ask the kernel to do something for us. The overhead of making those system calls, unfortunately, has grown in recent years. This is partly a result of vulnerabilities like Meltdown, which mean user space can no longer share page tables with the kernel. We have kernel page table isolation. The result of that is that switches from user space to kernel and back again are more expensive. You can demonstrate this by contrasting doing a large number of system calls with mitigations off versus mitigations on. So we take a simple system call like get PPID, call in a loop 1,000,000 times, measure the total time taken, and then divide by 1,000,000 to get the average time per call. And we can compare just a simple function call, a system call with mitigations off, and a system call with mitigations on. And what we see in a recent kernel is function call just takes a couple of nanoseconds. The system call with mitigations off takes about 95 nanoseconds, which is pretty quick. But then with mitigations on, we jump up to about 280 nanoseconds for that system call. So there's a bit of a growth there that you can see. There's long been efforts to reduce the overheads of such system calls. glibc used to cache things like process IDs and thread IDs. So get PID and get TID wouldn't actually require a system call. But there's problems with that, particularly forks and clones can invalidate the cache values when we're suddenly in a child process. So glibc caching was removed. And that removal caused problems too, because some containerized environments hadn't ever used a system call to get their PID, so that had to be added to the safe list of system calls. And systemd, which was a heavy user of get PID, saw some performance regressions too. Another method that's been used to reduce overheads is VDSO. So VDSO is something that's provided by the kernel. It's a virtual dynamic shared object. The kernel maps into the address space of processes. So we can see it there. There's the VDSO virtual memory area, and there's also an associated VVAR area as well, just ahead of it. So as I say, the VDSO is a shared library that's built by the kernel, mapped into the address space. And its job is to look up values in that VVARs area that the kernel populates. So the idea being, because we've mapped that VVARs area into the address space of processes, the VDSO functions can look up the values that the kernel separately populates. And we don't have that switch from user space to kernel and back again that costs us for system calls. VDSO currently supports timekeeping and retrieving CPU ID, and random number generation has been recently added as well. So glibc uses it by getting that VDSO base address and dynamically linking in the associated functions, and then we can call them in the system call wrappers to get the data that's cached in the VVARs area rather than actually having to make the system call when it's available. So when you look back at this picture, you might think to yourself, well, BPF can do a number of those things, and indeed it can. So we can use a BPF program to actually store values in BPF maps. And that sort of plays a role like vVars does for VDSO. And BPF programs can also update those values when events of interest happen. So, for example, you could update your cached UID when, say, UID succeeds for a process. And the nice thing is we can also retrieve those values in user space without a system call. So we can use direct memory access for map data as long as that map has been mapped into the address space of the user space process. So at the moment, array maps support that mapping. So if we have an array map and we map it into our process address space, we can access it without making system calls to retrieve that data. So that's a nice feature. So BySysCall is essentially just a proof of concept of this approach. We're working to open source it on GitHub at the moment, so stay tuned for that. It covers a few simple get-related system calls like get PID, get TID, get UID, get GID, and get usage. So there's a BySysCall service, and its job is to load and attach and pin BPF programs on our array map as well. And that's pinned as well to BPFFS. And then the BySysCall service just exits. So once we pinned all those things into the file system, they're not going to go away. And then to actually use BySysCall, we have to LD preload the libbysyscall library. And the reason for this is we want to override glibc's get PID, get UID, etc., with our own versions which look up cached values. So the LD preload that's essentially what that's there for, to make sure we use our own version of those functions rather than libc's. So to use it, as I say, just enable the service in the usual way, and then LD preload the library, and then you can just run whichever command you want to use. So for example, we can use Python in this case. So now when get PID is called from the Python binary, it will be the libbysyscall version, which avoids system calls where possible. So you can also enable stats. So this shows you which system calls you've avoided. So if you specify BySysCall log equals info as an environment variable, we can see here when we ran Python and just exited, we bypass get PID twice, get UID once, and get GID once as well. So we also want to assess the effects on performance, of course. So we created a simple program for each of these syscall bypasses. So for example, for get PID system call wrapper, we have a get PID program, which calls the get PID wrapper a specified number of times. Then it compares the result that we get to the raw system call to ensure that the answer that we get from our own BySysCall wrapper is right. So in a baseline case where we're not using BySysCall in the picture at all, we see if we call that get PID wrapper 10 million times, it takes about a second to do that in all. And about 2/3 of that time we're spending in the kernel. You can see the sys time there. And we can use BPF observability to confirm the system call profile is what we expect. So in this case, we see here in bold, we've got 1,001 get PID system calls for when we call that program with a parameter of 1,000. So the idea is we've called the wrapper 1,000 times and then once to verify, and we've called the system call one additional time to verify that we get the right answer. So in this case, we're not using BySysCall yet. So when we actually use BySysCall and do the LD preload, we can see the time is a lot quicker. So it takes less than 10 milliseconds to do 10 million get PID wrapper calls. And the difference there is we only spend about 1 millisecond in kernel. So we're not actually doing the system call. So we can verify that by using BPF observability again. In this case, we only see one get PID system call, and that's our raw system call that we use to verify that the answer we're getting back from BySysCall is right. So we focus for the first iteration on per thread caching of information for tasks. So BySysCall supports system calls that relate to that. So we're storing process ID, thread ID, UID, group ID, and usage data for get usage on a per task basis. So we have an array map. As we said, they can be mappable into user space. So that's used to store this info. So each element in the array contains all of that information. And we have an index variable, and that's essentially what user space is going to use to figure out for its particular current context, which element to look up. So that index assignment needs to be done. So it's done for when libbysyscall is first used, when we LD preload it. And when we fork from a libbysyscall using process, and when we pthread create from a libbysyscall using process, because in all those cases, we need a unique ID for the unique task that we're dealing with. So one question you might ask here is, rather than using an array map, could we not just use mapped per task storage? That seems like a nice fit for a problem like this. And there's proof of concept patches for this. But the problem with that is that every time we'd fork or create a thread, then it would become expensive because we need to actually explicitly mmap the memory associated with that task into user space. Whereas just updating an index value is a much more lightweight approach. So you can see here, here's the get PID implementation in lib by syscall. So we're looking to see if we have per task data, and if we do, we update the stats and then look up that per task data using our per thread index and get the associated process ID. Otherwise, we fall back to using the real get PID call. So this is what the architecture looks like. So we have BPF programs updating values as needed in a similar way to the kernel does for vvars. We have an mmap BPF array map with the indexes populated for a process with 2 threads and another process with 1 thread. So we have indices assigned to each of those tasks, which are used to look up the relevant values. So just quickly, we'll kind of demonstrate how we got to this point. So initially, when we LD preload our by syscall library, its first job is to essentially find that mmap to array map and mmap it into the user space of the process. So when we have an init function called by syscall init, which is called when the library is first loaded, and that's essentially what that does. But we also in the kernel have a BPF program tracing that by syscall init call. Its job is then to find a free array index in our array map, update the cached values in that array index, and then set the index in the user space process via BPF probe write user. So now we've got an assigned index which has populated data for this process and single thread. Moving on, we can fork from that process, and in this case, we actually have a uprobe tracing the return of the fork, where the return value is 0. That's when we're in the child process context. In that case, we need a separate array index again. So we find a free one, update the cache values, and set the index to 1 in the child process. And because we've got copy on write memory here, we've got a separate memory storage for the same index. So we can change that value there in the child process without affecting the parent. Threads are a bit more complicated. So in this case, we have to trace start thread, which is what the pthread library calls when it's starting to run a new thread. So in this case, again, we get an array index, update the cache values, and set the index value. We have to actually get the per thread variable address, and we get that relative to the pthread t that we're starting. So we can assign that value as well. So we've wound up with separate index values for each of these processes and threads, and we can look up the values then without actually having to make a system call because we've mapped the memory into the address space of the user space processes. So in future, we want to support more clone variants. There's a lot of flags to clone which can do complicated things, so you want to support all of those things. We also want to look at, of course, adding more additional system call support as well. So thanks for your time.
Thank you, Alan, for that fascinating talk. And there is, again, a thread in Slack. So if you have questions for Alan, please just go ahead and put them in there. So for the last talk before our final break of the day, we are going to turn to Chris Tarazi, also a colleague of ours at Isovalent, and he's going to be giving us a primer on eBPF map batch operations.
Hello, everyone. Welcome to my lightning talk on eBPF map batch operations. My name is Chris Tarazi, and I've been working at Isovalent for the past 4.5 years. Today, I'll tell you about the use cases and benefits of batch operations, some well-known, must-known gotchas, and how to use batch operations in your own application. First, what are eBPF maps? Without going into too much details, they are data stores for storing key value pairs that allow sharing data between kernel space and user space applications. What are the use cases and benefits of these? Well, they simply allow us to dump, initialize, and clear elements from a map at once, as opposed to element by element. This is beneficial as it can reduce the amount of system calls your application performs to the kernel, which reduces the amount of context switching between user and kernel space. The more you reduce context switching, the better performance your application will have. These next few slides will show the use cases and their corresponding API reference, but I won't go through each one just for time purposes, but these are here for reference. The main thing we will discuss, though, in this talk is that the API of these operations, as they look a bit complicated. Skipping ahead. How does Cilium leverage batch operations? The main usage of batch operations is to perform a batch lookup to efficiently measure eBPF map pressure and export that as a metric for observability. In the future, more operations can be converted to use batching besides just lookups, but we will dig into the map pressure metric calculation. So Cilium needs to be able to do this efficiently, and so therefore it uses the batch lookup. Understanding the map pressure is key to preventing issues when operating Cilium. Some maps in Cilium can be modified by both the agent and the data path concurrently. This means Cilium itself can't keep an accurate track of the map pressure. Therefore, we have to use the batch lookup call to count the number of elements periodically in order to compute the metric and then publish it. However, to use the batch lookup, Cilium must provide a buffer to store the keys and values of the map. But how do you know how to size these buffers? This is where we get into the gotchas. The gotchas of the current API is that it requires you to know some implementation details of particular map types in the kernel. We'll dig into case 3 here because maps of type hash tend to be the most commonly used type, but we'll come back to cases 1 and 2 later. So for case 3, how do you know how to size the keys and values buffers when using the batch lookup call, especially on a hash map to avoid the kernel errors, because it can't be too large and it can't be too small, but somewhere reasonable. The gotcha, though, to finding that reasonable value is that these keys and values are a user space buffer, and the size of them cannot be smaller than the largest bucket size of the kernel space hash map. If you do, the kernel will return an error. But what buckets are we talking about? Let's do a quick overview of hash tables to understand what we mean by buckets. Generally, hash tables are implemented using an array of linked lists, also known as buckets, and a hash function. In the kernel, this is no different. Upon insertion, elements are hashed and inserted into a bucket, as we see with key 0 going to bucket 1, key 1 going to bucket 0. When a bucket already contains an element and a new one's inserted, that's considered a collision, and the new element will need to be chained onto the previous, like we see with bucket 0 and bucket 4. Okay, going back to the gotcha of the user space buffer having to be larger than the largest bucket in the kernel space side of the hash map. But how can we possibly know what the largest bucket size in the kernel is? It's hidden inside the kernel. Well, it's basically impossible, but we can do an estimation where we have the square root of 2 times n, where n is the map capacity. And the map capacity here in this diagram is 7, so we have square root of 14, which is 4, after taking the ceiling, just to be safe. In the diagram, we see that the largest bucket size is 2, so we're good. We have a user space buffer size of 4, and the largest bucket size in kernel space is 2, so we're good in this case. In general, the solution to most gotchas is to use the Cilium eBPF library, as it hides a lot more of the API implementation details in the kernel. It removes details of handling the in and out batch correctly, and handles the array and LPM map types automatically. These are the first and second gotchas we skipped over in the previous slides. The hash type requires a bit more work, as we have to determine the keys and values buffer sizes, but I've shown you already how to handle that. Overall, the batch ops API is much easier to deal with using the library, especially with cursor abstraction. Here we have an example of doing a batch lookup to dump a hash map. As we previously talked about, we have the buffer size determined by the square root of 2 times the capacity. And notice the usage of the cursor here, which abstracts away all the complicated details in the API. And that's it. Here's a list of resources and acknowledgements. Thank you for attending my talk, and I hope it's useful for you.
Thank you, Chris. So as always, there will be a Slack thread to where you can post any questions you might have about eBPF map batch operations, and Chris will answer them for you. So we are going to go into our last break. When we come back from that break, it's our last set of talks, and it's going to end up with our final keynote of the day. So if you're looking forward to finding out about using eBPF with Java, then you'll be in the right place. So come back here at 20 past the hour when we will recommence our final block of talks.
Hey everybody, meet Bleppert, my smallest EV. This EB is actually assembled by my in-house Lego expert, my daughter Aviva. She's doing great work there. This next set of talks is actually talking about security from eBPF security rather than leveraging eBPF to improve security and other things or to create chaos or all of those wonderful talks we saw earlier in the day. This set is more talks on improving the security of eBPF itself, including the very first one, which is by Nathaniel Theus, talking about the security assessment of the eBPF verifier.
Hello, everybody. I'm Nathaniel Thies with NCC Group, and we're a global cyber and software resilience business that operates across multiple sectors, geographies, and technologies. We've been engaged by the Linux Foundation to assess the security of the eBPF verifier. This engagement is currently in progress. I'm a senior security consultant and part of our hardware and embedded systems team. I'm working with Chris Anley, our chief scientist, on this engagement. So eBPF is great because it's a lot safer than loading a custom kernel module. It's hard to get cases where you crash, say, hundreds of thousands of production systems with a single eBPF that has a bug in it. And yet it's still almost as fast as native code because it's JIT compiled by the kernel down to assembly at runtime. eBPF should be safe to use from unprivileged contexts, although it isn't always allowed by policy. So the kernel has to handle untrusted and potentially malicious eBPF programs, compile them down to assembly, and yet not insert a bunch of runtime safety checks that make everything slow. And to do this, the kernel statically verifies every time an eBPF program is loaded that it is safe. The verifier looks at every possible path through the program and makes sure that that path is safe on all possible inputs. If any path can't be proven to be safe, the program is rejected, and the kernel will refuse to load it. If that sounds like a complicated task, that's because it is. Verifier.c alone is more than 20,000 lines of code, which is comparable to the Project Gutenberg ebook of Moby Dick in text format. And the verifier bugs can have and have had a high security impact, container escape, LPE, local privilege escalation, and so on. So what does it mean to be safe, though, for an eBPF program? Well, for one thing, you can't just go around dereferencing, say, random pointers or so on. You need to make sure that they're valid. So you can't, essentially violate memory safety. But there's also other invariants that some of them are more documented than others. Just to give you an idea, there's a mechanism in BPF called referenced pointers, and a referenced pointer is one that has to be freed by the program before it exits, freed or released. This is statically checked by the verifier. If you don't free a referenced pointer, the kernel will refuse to load your program. The verifier is sound but not complete by design. It's okay if the verifier rejects some safe programs, but it's not okay to accept any unsafe programs. The verifier has to reject anything that's unsafe. It has to be sort of conservative in that sense. So look at prior work on the verifier. There's been previous security research. There's been more than 40 CVEs in the kernel that mention verifier.c. Again, just one file for the verifier. And of course, bugs aren't always assigned to CVE. And in fact, bugs aren't always disclosed to kernel maintainers at all. Sometimes they're exploited in the wild and nobody knows about them. But there's also been formal verification of some parts of the verifier. In particular, academic work that verified the range analysis component of it. So those parts have been proven correct in isolation as of the revision that was verified. But that doesn't necessarily mean that the verifier as a whole is correct or sound. There's also been work on dynamic testing and fuzzing of the verifier. So Google released Buzzer, which is their eBPF fuzzing framework. There's also state embedding verification, which is quite recent academic work from a few months ago that aims to add extra checks to bytecode programs generated during fuzzing to help to detect verifier bugs. NCC Group's approach here is manual source code review of the verifier and of some parts of the x86-64 JIT. We apply sort of our experience in exploit development and vulnerability research to this task to help us sort of analyze some of this quite complicated code. We're also doing a literature review of academic research and analysis of previous bugs that have been in the verifier. And another part of this is identifying and documenting some of those invariants the verifier has to prove. So not just memory safety, as mentioned. These results will be released later this year in our public report. So watch for that when it comes out. And that's all for this. Questions and answers will be in Slack. I will be hanging out there. And thank you very much for your time.
Thank you very much, Nathaniel. NCC Group has done just an amazing amount of work. I know that we've used them to do security assessments of a variety of different projects in the CNCF. It's been just really impressive, including things like Kubernetes and lots of other great projects. Our next talk is by Soo-Hee Lim, talking about towards secure kernel extensibility with eBPF.
Hi everyone, my name is Soo-Hee. I'm a PhD student at the University of British Columbia, and today I will talk about how we use isolation techniques to ensure safe kernel extensibility with eBPF. eBPF lacks runtime memory safety. The implementation bugs in the eBPF verifier allows attackers to load malicious eBPF programs into the kernel. This allows attackers to gain arbitrary kernel memory access, such as overwriting kernel data and leaking kernel memory to the user space. Because the eBPF verifier is unsound, relying on static analysis alone is insufficient to guarantee runtime memory safety. Therefore, we implemented SafeBPF. It is a mechanism that dynamically sandboxes eBPF programs with software fault isolation and hardware-assisted memory tagging to enforce spatial memory safety at runtime. In SafeBPF, eBPF programs run in a sandbox, which is a region of memory that contains all the data an eBPF program can access. For software fault isolation, we generate 2 address masks for each sandbox, and we mask every load and store instructions so that when there is an out-of-bounds memory access, we can ensure that all memory accesses will always fall within the eBPF sandbox. Another isolation technique we implemented is memory tagging with ARM memory tagging extension, MTE. So memory tagging usually happens during memory allocation. And with ARM MTE, every 16 bytes of the physical memory is associated with a tag. During memory access, the hardware will check if the tag in the pointer matches the tag in the physical memory. If there is a tag mismatch, the kernel will raise an exception. And the way we use ARM MTE to sandbox the eBPF program is that we let the eBPF programs use a separate tag from the kernel, so that when the eBPF programs tries to perform an out-of-bounds access into the kernel memory, we are able to detect and prevent them at runtime. We evaluated SafeBPF on 7 high-severity vulnerabilities, and SafeBPF successfully prevents them. SafeBPF is also evaluated on web server macro benchmarks, and it incurs 0 to 4% overhead overall. The proceeding of this work will be available at the Cloud Computing Security Workshop 2024. And if you're interested in my work, you can contact me by my email. And we also have other eBPF projects available on my website. So for example, we've used eBPF to implement secure namespace kernel auditing for containers. And we've also used eBPF to customize prefetching policies in the Linux kernel. I'm open to collaborations, and I'm also looking for internships. So if you're interested in my work, please contact me. Thank you.
Thank you, Sui Lim. They are in the chat. Feel free to ask any questions. And I'm super excited to see like students working in this space as well. You know, it's like since I've been working at Cilium now for quite a while, and I will say that like it's been amazing to seeing like new people get involved over and over again within this community and across the whole entire community, whether in eBPF specifically or across the Cilium project, everywhere. It's just awesome. Our next talk is going to be from Juan Jose Lopez Jaimez, talking about lessons from the buzz.
Hi everyone, thank you for coming for my talk, Lessons from the Buzz, what we have learned so far from fuzzing the eBPF verifier. My name is Juan Jose. I've been a software developer at Google Montreal for 6 years. I've been doing cloud modernity research for the last 3 years. I'm currently going through a kernel hacking phase, and I'm going to talk to you about Buzzer. So we're going to talk a little bit what is Buzzer, why we wrote Buzzer, and what we have learned so far. So Buzzer is a tool for writing eBPF programs and to fuzzing the eBPF verifier. And the goal is to find logical bugs in the eBPF verifier. Now, I say here logical bugs because we don't focus on things like memory corruption bugs, as scholars are really doing a great job at that. So we figure we will focus more on the finding holes in the verification process of the verifier to be able to load programs that do things that were considered safe at verified time, but could result in potential security implications. So why do we write Buzzer? The eBPF verifier is very complex, and so is finding bugs in it. Last time I checked, which was today, it had around 20,000 lines of code. It has a very complex purpose, and you only need to state its purpose in words to understand how complex it is, like to make sure that the eBPF program is safe to be loaded into the kernel. And this is no easy task because, of course, you need to keep track of the state of your registers at every single point of execution. Like this includes branches. This includes also calls to helper functions or to kernel functions. Another thing is that this Buzzer was inspired by research that Simon Scannell, my colleague, did on his blog post. And also, Buzzer provides an alternative way to write eBPF programs at a low bytecode level instead of writing them at a higher C and then compiling it with Clang to produce the eBPF program. For me, particularly, being able to write eBPF programs at a very low level helped me understand more the internals of eBPF, how the verifier works, and that's how I develop a lot of the features that are present today in Buzzer. For me personally, this was one of the best ways I could have to learn how eBPF really works before I had little to no exposure. Of course, that's personal. Some other people may have other ways of learning. Now, another thing that I want to talk about is that, well, some of you may say, okay, why bother about doing research on eBPF if now unprivileged users cannot load eBPF programs, which is true. And I think this was the right decision to take back in 2021, 2022, if I'm not mistaken. However, I will also argue that eBPF adoption is growing, and that means that adversaries, when I think of it as an adversary, I think it's completely possible that eventually, or even now, I could land in a space that has CapBPF, a process or a container, get code execution there. And then suddenly I have this whole space in front of me, this whole attack surface in front of me to escalate my privileges. So making sure that we have a secure verifier means we are paving the security of eBPF for future adoption. And finally, because it's fun, like it's really satisfying to find a logical bug in the verifier and to write the exploit for it, particularly because it's very easy to write an exploit for it. Like if you were writing an exploit for like a use after free in the kernel. And as I say, like a bug in the verifier means you have a way for escalating your privileges. This is the screenshot of an exploit I wrote a couple of months ago, back in June, where we exploited one of the bugs we found with Buzzer. We escalated our privileges all the way to root. Of course, here the exploit has got BPF and it's more for illustrative purposes rather than like a fully weaponized exploit. Now let's jump into what we have learned so far. I'm going to talk about a few bugs that we have found with Buzzer, two of them. The first one, the very first bug that Buzzer found, we cover the complete details of it in our blog post. You can find it there. I'm not going to go into what it was or what happened exactly for time purposes, but in a nutshell, Buzzer found that one of the features of eBPF verifier, which is branch pruning, could lead to some paths of the program being overlooked by the verifier. And then if those paths had operations that could result in security implications, an attacker could go ahead and exploit those conditions. Okay, now what does this mean? Like the verifier, one of the things that it does is for optimization purposes, if it finds out that your program can reach an exit condition safely through a branch, and then it finds another branch that is similar or equivalent to this previously proven safe branch, then you will just assume, okay, this equivalent branch is also safe, therefore we're not going to explore it, we're going to prune it. There are a few cases where this doesn't happen, and that's where registers that are marked as precise are involved. If a register is marked as precise, the verifier is going to explore that branch no matter what. And usually sources of the registers being marked as precise is things like pointer arithmetic or things that require a little bit more care into making sure that the things are done right. Now, the bug CVE 2023-2163 pretty much can sum up as some of those registers involved into pointer arithmetic were not marked correctly as precise, and this led to certain branches of verifier being pruned and therefore deemed safe, where in reality they were not. And we wrote a proof of concept exploit that was a local privilege escalation and contained an escape out of it. What did we learn out of this? Well, first of all, the verifier is very complex, has a very complex job to do. And a lot of my colleagues and I agree that this bug will have been extremely difficult for an analyst, a security researcher, to find by hand, just because keeping track of the multiple states with multiple levels of nesting, branching into the verifier is a very hard job to do. And also that branch pruning remains a very good source of vulnerabilities or bugs for eBPF. Like if someone were to start in this space, I would recommend taking a look at branch pruning or keeping a close eye into branch pruning for the future bugs. I wouldn't discard that there are no more bugs there, although we're yet to find a new one. Then the next one, and the most recent one, which is 2024-41003. This is a fairly new bug introduced in kernel 6.8. It was possible to fool the verifier register limit tracking. I call this a more traditional eBPF verifier bug. Basically, we found out that in branching operations, we could corrupt the limit tracking of the verifier to make it off by 1, such that at verified time, the assumptions will be that the register has value of 0, but at runtime, the actual value will be value of 1. And just this little off by 1 discrepancy is enough to write a full-on local privilege escalation exploit. Now, what did we learn out of this is that software is constantly evolving, of course, and this evolving nature means that there are going to be bugs. Even in well-understood areas. And this is why having tools like fuzzers or rigorous testing is important, because we can catch these bugs before they're more widespread. For eBPF fuzzing, we also figured out that as of now in the state of Buzzer, it's not sufficient to rely on the signals that you get in the fuzzer, but also it's very good to have to pay close attention to other side channels like the verifier log. So the story behind this bug is that we're testing some new strategies based on coverage in Buzzer, and we noticed some weird logs about invariant violations when the coverage started to get after a certain point. And after inspecting those logs more closely and reproducing them, we found this bug. But this also means that at Buzzer we have a problem that's yet to be solved, which is like, how do you compare what the verifier thinks at verified time versus what actually happens at runtime? And this is one of the areas of future research that I propose is like, is there a way where we can extract the verified assumptions of the state of the eBPF registers and compare them with what actually goes down at runtime? If we were able to get that information, we will be able to fuzz eBPF verifier much more efficiently. We're yet to solve this problem in Buzzer. And now with this summer, we had an intern helping us implement eBPF support, Alanis Negroni. Thanks to her contributions to the project, now we have access to BTF information, which opens the door for more advanced features like kernel helper functions. Another future research idea is like have better coverage guiding fuzzing. Coverage guided was the feature that helped us discover the most recent bug. And of course, once eBPF on Windows arrives, it'll be interesting to take a look at that from a Windows perspective. That's about it. That's about all the time I have for you. So let me know if you have any questions, and thank you for attending.
Awesome work, Juan. I actually really like that quote. You know, by learning how to break it, I learned more about how it works. You know, like that's amazing. Like it's a really good way of looking at how like some of these more complex technologies work. If you can figure out how to push the edges, see what things are, you know, if you have that what if in your mind, then that really kind of unlocks what could be possible. That is all of our talks. So far, all of the talks so far, we have one final keynote for you, which is going to be by Johannes Brockberg, talking about writing a Linux scheduler in Java with eBPF.
Hi, I'm Johannes Bechberger, and in this talk I'll be showing you how to write a Linux scheduler in Java with eBPF. In my day-to-day work, I work on the OpenJDK, so I work directly on Java, but today I'll be showing you how to write your own Linux scheduler in Java with eBPF. But first of all, what is scheduling? So what scheduling is, it solves the problem that you have multiple processes on your system and multiple CPUs, and you want to run all these processes at the same time, but you can't, so you have to decide which process comes onto which CPU core at every point in time, and that's called scheduling. So consider we have two processes, process A and B, and only one CPU core. So a simple scheduling policy would be just to let process A run all the time. The only problem, process B would be starving, which is not that great. So what typical schedulers would do, they would, for example, start with scheduling A for a specific time slice, then scheduling B, and so on. And maybe process A has a higher priority than process B, or process B can only wait on I/O, so the scheduler decides to schedule A again, and then maybe B again, and A again at the end. And this ensures that process B and A are responsive and can run alongside each other. So what I did now, I created a project where you can simply implement a Java interface called scheduler and implement a few methods that relate to scheduling, and then have your own Linux scheduler written in Java. And the cool thing is this runs on this machine. So you see here, these are the current statistics updated every 5 seconds for this machine, printed by the user level part of the scheduler. So what is the performance? It's actually not that bad. I didn't see any negative effect on the performance while running a typical Java benchmark, and it runs good enough in common use cases. But of course, it's not as responsive as a proper scheduler would be. But why would you write the scheduler, and why is it good that it's now possible with SCADX to write your own scheduler? To quote Tajan here, one of the developers of the scheduler extensions for Linux, it assures an ease of experimentation and exploration, so you'll be able to easily experiment with different scheduling policies. It allows you to customize your scheduling policy, for example, to target your own needs, because the common Linux schedulers, they were good for a broad range of applications, but they might not optimal for your current situation because they don't have domain knowledge on your current situation, of course. And of course, because it's all written in eBPF, as the title suggests of this talk, you can rapidly deploy different schedulers without restarting your system, which is pretty decent. But how does it work under the hood? So what you have Java code, and parts of it will be run in user land and parts in kernel land. And the code run in kernel land essentially allows you to describe C code and Java code. So you have this part of the Java code then compiled down to C code via my project Hello eBPF, and then the C code is compiled to eBPF bytecode and is loaded into the Linux kernel via the libbpf, and then attached to the scheduler extensions to create your own scheduling policy. And these then schedule all the processes. And of course, also the process on this very system where I'm doing this presentation. Now you probably want to know all the code, and here it is. So I start with the base structure. You have a class, I call it here sample structure, and this class extends the eBPF program and implements the scheduler. We first define our scheduling QID because we want to have our own, and then we define some types. Here we define the type stats, which essentially contains the stats that relate to store per CPU and whether the process on it come from a local or a CPU global queue. And then we have to initialize our scheduling queue by SCX BPF create DSQ. And what we do here, we overrode the init method of the scheduling interface and thereby providing the scheduler with this function. Then we also want to define some eBPF maps, essentially for statistics, and these are the statistics that you saw before printed on the command line. And then what we also want to do, we want to select the CPUs for every task, and this is done by internal methods, but usually what one would do is to check, hey, is the CPU that I selected idle, so it's currently not executing anything? If yes, then we can directly dispatch the process on the CPU and go like the fast track. Of course, we also have the case where a process is enqueued, where a process wants to run, and we first increment some stats and record the enqueue, so gather some information that we later log, and then we just dispatch it to our queue that we created before. And every time a CPU wants to run something because it's the previous process finished its time slice, just call SCX BPF consume and tell it, hey, just consume a new task from this queue. But you may ask, why would you write this whole thing in Java? And of course, the simplest answer is why not? I think eBPF is currently in the phase of exploration, where many people try interesting things out, like creating their own schedulers or creating their own firewalls. But also it probably will help in the future people with testing, because testing Java programs for things like race conditions or deadlocks, it's pretty difficult and it's hard to reproduce these concurrent settings. But if you control a scheduler, you can essentially quite easily create a library combined with a normal testing library like JUnit in Java case to better be able to test concurrency bugs. And that's pretty awesome. And also to reproduce them later to check that they didn't occur before, because you essentially can control the scheduling order of the processes and thereby of your Java threads, for example. You might also want to know whether we can already use it, because I teased that it's in the scheduler extensions. So when will the scheduler extensions be part of the Linux mainline kernel? Because they aren't yet. Of course, you can get a patch kernel. You can compile it yourself or install the CachyOS operating system that I'm currently using to use these kernels. But in reality, you probably want to wait till it's in the mainline kernel. And it's not yet there, but when Linus Torvalds was asked a couple of weeks ago when it will be merged, He answered at the Open Source Summit in Asia, "I will not vote because I was sure it was going to be in 6.11, but yes, looks like we're now looking at 6.12. So it will probably be in 6.12. It's unsure whether there will be features, and they'll probably be missing some features that you might want to use for more complex schedulers, but still you can probably in a couple of months be able to use a standard mainline kernel to do this, and that's pretty awesome in my opinion. And of course, the underlying library that they developed for running eBPF applications from Java and for compiling some Java code down to C code is called Hello eBPF. As I told you before, and it's the library that they created in the last 8 months. It's still a prototype, but it shows some promise because it allows you to write, as you've seen, eBPF applications directly in Java without writing that much C code in a string. And that was it all for me. I hope you saw now that writing schedulers is possible in Java with eBPF. If you want to learn more, I just wrote a blog post that's on my blog, mostly_nerdless.de, that you find under this QR code that I've presented on this very topic, where you see all the information and all the links. I myself want to say thanks to Dylan Reimer, who helped me with the whole eBPF library, and also to the people from the SCADX chat. They are pretty lovely and they answer every question. That's pretty cool. And of course, I want to say thanks to my team at Submachine that allowed me to do this as a side project. And thanks to you for coming with me on this short journey. And maybe I see you somewhere else soon. Bye.
Great talk by Johannes, talking about all things SCADX. I know that's been some drama getting into the kernel. It's great to see the work that's happening there. Johannes is in the chat with us, answering questions, the sort of stuff. That was our last keynote of the day. In the very next section, we're going to revisit the CTF and kind of get an update from the awesome team about how all of that's going.
So welcome, Dan. Can we hear you this time? That's the question.
I'm hoping so.
Yes, we can.
Okay. Yes.
Yes, we can hear you.
I'm
All
so sorry
right.
about that.
So for anyone who wasn't watching earlier, praying to the bee gods. Yeah, we had some technical difficulties earlier with Dan's sound, but now we're good. So Dan has been responsible for putting together this year's Capture the Flag Challenge, and he has also been keeping an eye on how people have been getting on. So has anybody cracked it today?
Yes. So I don't know what I was more nervous about, whether my audio was going to work or whether somebody was hopefully going to get to the end of their Capture the Flag Challenge. So yeah, it's been in people's hands for about 4 hours. As soon as the conference was, as soon as the summit started, somebody already kind of found the challenge that we'd kind of open sourced minutes before, so people were trying to jump on it. And yes, in the end, somebody has managed to complete the Capture the Flag Challenge. So I'd like to give a big shout out to Leonard Conan, who managed to complete the CTF in 1 hour, 46 minutes and 59 seconds. So fantastic work there, going through all of the various challenges that made up the Capture the Flag for this year.
That is brilliant. I've put up the QR code, so if anybody hasn't already found the repo and wants to give the challenge a try, you still can, because you can do it in your own time. And there are 4 great challenges that progress in difficulty. So definitely recommend stretching your eBPF skills with those challenges. Yeah. Now, we're not going to give away how people have solved it today, but I believe you are going to be giving it away on Friday, right, Dan?
Yes, that's correct. Yeah. So there's still a number of people who are working through the CTF right now. And if you don't make your way through to the end of it today or through the rest of the week, then on Friday in our Echo office hours, we're going to be stepping through all of it from start to finish. So we'll kind of step through the thought process of, kind of how we came up with the actual challenges themselves, what's actually kind of happening on the back end. And then we'll go through them from either a operations perspective using things like BPF tool, or we'll step through the actual code samples that you would use in order to answer the various challenges that are presented to you through the CTF. So if you have questions, if you've gotten stuck with any areas on that, please come join me on Friday with your questions and where you got to. And we'll walk through why things don't work as you'd expect them to.
Fantastic. So if you want to come to Dan's session about solving the CTF, it's going to be in the eBPF and Cilium office hours on Friday, 2 p.m. UK time. It's on the same eBPF and Cilium community YouTube channel where you are probably watching the eBPF Summit right now, but I have put up the QR code so you can find that link again. You're probably already there, but just in case.
Yes.
So I think with that said, why don't we bring back Duffy? And I guess we're going to close out the show. I mean, maybe Duffy, what's been your favorite talk of today?
Gosh, there's been so many. I have to say I was kind of pretty impressed with some of the security talks. Not really about like eBPF security, although those were amazing. I was talking about more like how, with the context that we're able to get with CTF, with eBPF, we can actually make kind of better decisions and understand more about what's actually happening on that threat landscape. And I thought that was amazing. Like the car talk was amazing. There are just so many awesome talks.
That car talk really blew my mind too. Yeah. Dan, any other highlights you want to mention?
Yeah, I think for me, really, I really enjoyed the section talks that we all kind of had around the verifier, largely because I've been kind of answering questions from people who have been fighting with the verifier as part of the CTF without giving too much away. But yeah, it's amazing. I mean, I spent a lot of my time fighting with the verifier. And like the fact that people are writing buzzers to kind of fuzzers even to try and trick the verifier into doing things that it was never designed to do. Yeah, I'm loving all the work that's in that space.
Terrific. I have one more bee. I don't know if you found any more bees around your respective locations, but this one's pretty special, I think. Only problem is it's not cold because it's been sitting on my desk, so I'm not sure I can open it quite yet.
Awesome. And speaking of bees, we should give one more big shout out to all the people that have helped make this possible. Everybody from the program committee to Carla, to Dan, to you. I mean, everybody in the chat that's actually making our community feel very welcoming and feel interactive. Thank you all so much for being here and being a part of it. We couldn't do it without you.
Yeah, absolutely. It's wonderful to see the interactions on Slack and all the kind of comments and questions that have been flowing and the emojis. And yeah, absolutely. Thank you to everyone who's been behind the scenes. I just posted a message in Slack as well, naming just a few of the people who've really been helping make this event a reality. And it's been a lot of fun. So I hope people have enjoyed watching it, even half as much as I've enjoyed being part of presenting it. Then that will have been a huge success.
Yep. We'll see many of you in Salt Lake City.
Absolutely, for KubeCon. So with that, bye everyone.
Bye.